In 1600 BC, you stand beneath a night sky above ancient Mesopotamia, where darkness feels deeper than anything most people experience today. There are no electric lamps glowing beyond the horizon, no aircraft cross the stars, no satellites drift silently overhead. When evening settles across the mud-brick cities beside the Euphrates, the universe seems to descend almost to the rooftops. You hear sandals brushing dusty streets and animals shifting behind courtyard walls. Smoke from cooking fires carries the smell of wood, grain, and warm earth. Above you, thousands of stars appear with a clarity that modern city dwellers rarely encounter. And somewhere among those lights lies a secret nobody around you could possibly imagine. The universe had a beginning. Everything you can see, every star, every planet, every grain of dust beneath your feet, emerged from a cosmic history stretching backward toward an extraordinarily hot and dense early state. But you do not know that yet, for now there is only the sky. Long before humanity asks when the universe began, you first have to notice that the heavens change. The discovery sounds simple, almost embarrassingly simple, yet it requires generations of patient observation before patterns become knowledge. Imagine yourself living thousands of years before telescopes, clocks, or printed calendars. Your most reliable celestial instrument is your own pair of eyes. The sun rises somewhere along the eastern horizon each morning. Its position changes gradually through the year. Shadows lengthen and shorten. Certain stars disappear for months, then quietly return. The moon performs an even more obvious transformation. You watch its thin crescent grow, night after night, becoming half illuminated, then nearly circular. Eventually it becomes full, casting pale light across fields and pathways. Then the process reverses. You can feel cool night air against your skin while watching this slow celestial rhythm. For agricultural communities, these patterns are not merely beautiful, they matter for survival. Knowing approximately when seasonal rains arrive can determine when crops are planted. Recognizing the changing position of the sun helps organize agricultural work. Lunar cycles provide convenient units for dividing stretches of time. The sky becomes humanity's enormous natural clock. Yet practical observation and imagination remain closely intertwined. You cannot touch the stars. You cannot travel toward them. You have no instruments capable of revealing their physical nature, so you explain them using familiar things. Across ancient cultures, celestial objects become associated with gods, ancestors, animals, heroes, spirits, and cosmic stories. These interpretations differ enormously between societies, but the impulse behind them is recognizably human. You see patterns because patterns help make uncertainty manageable. Perhaps that explains why constellations become so compelling. The stars forming a constellation are usually unrelated objects separated by immense distances, yet from Earth they appear arranged upon a single dark surface. Your mind connects them. A few bright points become a hunter, a bull, a lion, or another familiar figure. The night study contains characters and stories. There is something gently amusing about this habit. Humanity spends thousands of years drawing imaginary lines between unrelated stars, then eventually builds spacecraft using mathematics precise enough to navigate between planets. Both activities begin with looking upward. Ancient sky watchers also noticed several lights behaving differently from ordinary stars. These objects wander against the background constellations. Today you know them as planets: Mercury, Venus, Mars, Jupiter, and Saturn can all be seen without telescopes. Their movements are slow enough to reward patient observers and strange enough to demand explanations. Mars sometimes appears to reverse direction temporarily against the stars. It does not truly reverse its orbit, but from a moving Earth, the geometry creates that appearance. To an ancient observer, however, Earth does not feel as though it moves. You stand on solid ground. Nothing beneath your feet suggests that your world is rotating rapidly while traveling around the sun. A bird can leave a branch without being hurled westward. A dropped stone falls almost directly downward. The obvious conclusion seems unavoidable. Earth is still. The heavens move around you. This idea will eventually become part of sophisticated cosmological systems, but its origins are grounded in ordinary experience. Ancient people were not foolish for accepting it. They were reasoning from the evidence available to their senses. Even stranger events occasionally disturb this ordered sky. A lunar eclipse slowly darkens the moon. A solar eclipse can transform daylight into an eerie twilight. Birds may become quiet. Temperatures fall slightly. Shadows sharpen into unfamiliar shapes. You can imagine the atmosphere among people who have never received a scientific explanation for such an event. The familiar sun appears wounded. Then it returns. Different cultures interpret eclipses in different ways, sometimes religiously and sometimes politically. Yet repeated observation gradually reveals that even these frightening events possess patterns. This realization matters enormously. The heavens are not merely unpredictable theater. They can be studied. Archaeologists and historians still debate how confidently particular prehistoric monuments should be interpreted as astronomical observatories. Some structures clearly possess celestial alignments, while claims about elaborate prehistoric astronomical systems remain harder to establish. Stonehenge offers a famous example. Beginning roughly 5,000 years ago, communities in Britain constructed and modified the monument across many generations. Important parts of its architecture align with significant solar directions associated with the solstices. You can imagine standing there during midwinter. Cold wind moves across Salisbury Plain. Damp grass brushes your legs. Smoke from nearby fires hangs faintly in the air while people gather among enormous stones. The sun approaches the horizon at a meaningful point. What precisely every participant believed is lost. The stones cannot explain themselves. That uncertainty is worth keeping, because ancient astronomy was not one universal system. Different societies watched the same heavens while constructing different meanings around them. Meanwhile, the physical universe remained completely indifferent to human interpretations. By the time these communities watched the solstice sun, the universe had already existed for roughly 13.8 billion years. Our solar system was about 4.6 billion years old. The sun was already converting hydrogen into helium within its core, releasing the energy that warmed those observers standing beneath the winter sky. Yet nobody knew what the sun was. Nobody knew stars were distant suns. Nobody knew Earth was a planet. Nobody knew there were galaxies. And certainly nobody suspected that space itself could expand. The physical story of the universe had unfolded almost entirely without witnesses capable of understanding it. Hydrogen and helium had formed during the early universe, Gravity had gathered matter into the first stars and galaxies. Generations of stars had manufactured heavier elements inside their interiors and explosive deaths. Eventually, those elements became part of new stars and planets. Some became Earth, some became you. There is a quiet irony here. The ancient observer looking upward is made from material forged through cosmic processes that observer cannot yet comprehend. Carbon within the body originated through stellar nuclear reactions. Much of the oxygen around you has a similarly ancient stellar history. The calcium in bones belongs to this long chain of cosmic recycling. You are not simply observing the universe. You are part of it becoming curious about itself. Still, that understanding remains unimaginably distant. For now, knowledge advances through smaller discoveries. Someone notices that a star rises shortly before dawn during a particular season. Someone remembers where the moon appeared several nights earlier. Someone realizes that the length of a shadow changes predictably. Observations become traditions. Traditions become records. Records eventually become astronomy. There are also stranger traces of humanity's fascination with the heavens. Ancient objects sometimes contain groups of marks that researchers have proposed might represent lunar cycles or celestial patterns. Such interpretations remain controversial. A row of scratches can be a calendar, decoration, counting system, or something entirely different. Prehistory rarely provides convenient explanatory labels. The uncertainty itself tells you something important. Human curiosity about the sky is probably older than written astronomy, but reconstructing its earliest forms requires caution. You cannot simply place modern knowledge inside ancient minds. Instead, you follow the evidence slowly, night after night, generation after generation. People begin separating repeating celestial behavior from unexpected events. The sky acquires structure. That structure will eventually become mathematical. Thousands of years later, equations will describe galaxies moving through expanding space. Instruments will detect radiation released when the universe was only hundreds of thousands of years old. But those discoveries depend upon a much older habit. You look up, you remember what you saw, then you look again. Along the great rivers of Mesopotamia, that habit is about to become something more systematic. Observers will begin preserving celestial events across generations, turning the changing heavens into records that can outlive the people who made them. The universe has been shining for billions of years. Humanity has finally started keeping notes. You remain beneath the same ancient sky, but the relationship between humanity and the heavens is becoming more disciplined. Across Mesopotamia, generations of observers begin doing something remarkably powerful. They write down what they see. The transformation seems modest at first. A planet appears near a particular star. The moon disappears during an eclipse. Venus rises before sunrise on certain mornings. Someone records the event. Then someone else reads that record years later. Memory has escaped the human lifetime. In Babylon, particularly during the first millennium BC, astronomical observation becomes increasingly systematic. Scribes preserve records of lunar movements, eclipses, planetary positions, weather, prices, river conditions, and other events. You can imagine entering a quiet working room after sunset. Oil lamps flicker against mud brick walls. The air carries faint smells of smoke, clay, and warm dust. A scribe presses a reed stylus carefully into a small tablet of damp clay. Outside, the city murmurs. Above the rooftops, Jupiter shines. The tablet seems insignificant compared with the planet, yet something profound is happening between them. A human being is converting celestial motion into information that can survive for centuries. Babylonian astronomy develops partly within a religious and political culture that treats unusual celestial events as possible signs. Kings want to know what eclipses might mean. Priests and scholars search for patterns connecting the heavens with earthly affairs. Modern astronomy will eventually abandon celestial divination, but the careful observations associated with these traditions become extraordinarily valuable. It is an unusual historical partnership. Beliefs that modern science rejects can still encourage measurements that later science finds useful. You begin to understand why scientific history rarely moves along a perfectly straight road. Babylonian observers become particularly skilled at recognizing repeating cycles. They learn that lunar eclipses are not random interruptions, but events whose recurrence can be anticipated. One famous pattern is now called the Saros cycle, lasting roughly 18 years and 11 days, with some variation depending on leap years. After that interval, similar arrangements of the Sun, Earth, and Moon return. An eclipse does not simply repeat over the same village, because Earth's rotation shifts where the event becomes visible. Yet the cycle provides a powerful framework for prediction. Imagine how extraordinary this feels without knowing orbital mechanics. You cannot see Earth moving through space. You do not know gravity controls the Moon's orbit. Yet careful records reveal hidden regularity behind apparently mysterious events. Prediction begins before explanation. That pattern will appear repeatedly in astronomy. Sometimes humanity learns how nature behaves long before understanding why. Babylonian scholars also develop mathematical methods for tracking planetary motion, rather than constructing physical models resembling later Greek cosmology. They often focus on calculating celestial positions through numerical procedures. The distinction matters. You do not always need to know what something is before measuring what it does. A planet may remain mysterious while its movements become predictable. This patient mathematical tradition provides later astronomers with an enormous inheritance. Some surviving clay tablets preserve astronomical information with astonishing detail. One particularly curious example shows that Babylonian scholars could use sophisticated geometrical reasoning to describe Jupiter's changing motion. For a civilization often imagined only through temples and kings, this is a wonderfully inconvenient reminder that ancient intellectual life was complicated. People were calculating planetary behavior while most of the world still lacked written records. Yet historians continue debating how particular mathematical techniques developed and how widely specialized astronomical knowledge circulated among scholars. Surviving tablets represent only fragments of enormous traditions. Most ancient conversations vanished. Most calculations disappeared. You are listening to history through scattered pieces of clay. Farther west, another civilization builds its relationship with the sky around a very different landscape. You travel toward ancient Egypt. The smell of dry desert air gives way near the Nile to damp soil, vegetation, animals, and cultivated fields. The river creates a narrow green corridor through an otherwise arid world. Here, time matters deeply. The annual cycle of the Nile shapes agriculture and social organization. Egyptian calendars develop through interactions among seasonal change, religious traditions, administrative needs, and astronomical observation. The star Sirius becomes especially significant. Its annual heliacal rising, its first visible appearance shortly before sunrise, after a period of invisibility, became associated in Egyptian tradition with seasonal renewal and the Nile cycle. You stand near the river before dawn. The air is cool against your arms. Reeds rustle softly beside dark water. The eastern horizon gradually changes from black to deep blue. Then a bright point becomes visible. For someone watching year after year, the appearance is not merely beautiful. It helps anchor celestial observation to terrestrial time. Egyptian observers also divide portions of the night, using groups of stars sometimes known today as decans. Different stellar groups rise in sequence as the night progresses. The sky becomes a clock again. Only now, the clock is becoming more carefully organized. Astronomy appears in architecture and religious practice as well. Temples and monuments sometimes possess orientations connected with celestial or cardinal directions, although individual alignments require careful interpretation. It is tempting to imagine every ancient structure as a giant astronomical machine. Usually, reality is less tidy. A building can have practical, ceremonial, political, and astronomical significance simultaneously. Scholars still disagree about the intentions behind some orientations and how consistently celestial considerations governed particular construction projects. Ancient people did not divide life neatly into modern categories. Astronomy was not isolated from religion. Calendar making was not isolated from agriculture. Mathematics was not isolated from government. The sky touched almost everything, and still, nobody is asking about a Big Bang. The intellectual tools needed for that question do not yet exist. Even the concept of a universe evolving through physical time would feel strange within many ancient cosmologies. Creation might belong to mythology, divine action, recurring cycles, or philosophical speculation rather than measurable cosmic history. What people can measure is movement. The sun returns, the moon changes, planets wander, stars rise seasonally, eclipses recur. These repeating patterns naturally encourage an image of the heavens as cyclical rather than evolutionary. Nothing visible suggests that the universe itself once possessed radically different conditions. When you look at Orion tonight, it appears essentially unchanged from the Orion seen by your grandparents. Saturn moves slowly, but Saturn returns. The heavens seem permanent. This impression will survive for an astonishingly long time. Even many scientists, thousands of years later, will prefer an eternal or static cosmos. The idea that the entire universe possesses a physical history will require evidence that ancient observers simply cannot obtain. Yet those observers are quietly preparing the way. Measurement accumulates. Numbers become portable across generations and civilizations. Babylonian astronomical knowledge eventually influences Greek astronomy, directly and indirectly, particularly through numerical observations and methods connected with celestial cycles. Ideas travel with merchants, conquerors, scholars, manuscripts, and languages. Knowledge rarely belongs permanently to one culture. It moves. Sometimes it is preserved by people who disagree with its original interpretation. Sometimes an old observation waits centuries before becoming useful for a completely different question. This will become essential to the story ahead. To discover that the universe expands, astronomers will eventually need precise measurements of distant galaxies. To interpret those measurements, they will need mathematics, physics, instruments, and an assumption inherited from these ancient observers. Nature contains patterns worth recording. You step outside again. Night has deepened over the river valleys and cities. Somewhere, a scribe finishes another line before setting aside the stylus. Perhaps the tablet records an eclipse. Perhaps it notes a planet against the stars. The clay begins drying beneath human fingertips. Overhead, the Milky Way stretches across the darkness as a pale, luminous band whose true scale remains completely unknown. Nobody realizes that the glowing strip is an immense stellar system. Nobody realizes other galaxies lie far beyond it. Nobody knows space itself has a history. But humanity has learned something almost as important. The sky can be measured. Soon, another group of thinkers will begin asking a different question. They will not be satisfied merely knowing where the wandering lights will appear. They will ask what kind of universe could make them move that way. The records continue accumulating, but around the Mediterranean, another habit of thought begins changing the cosmic question. You move gradually into the intellectual world of ancient Greece, where inherited observations meet geometry, philosophy, argument, and an extraordinary appetite for constructing models. The evening sky itself has hardly changed. You can still watch Venus glowing near the horizon. Mars still wanders among the constellations. The moon still crosses the darkness with familiar regularity. What changes is the question. Instead of asking only when celestial events will occur, some thinkers begin asking what physical arrangement of the cosmos could explain them. You stand beside the Aegean on a quiet evening. Salt hangs faintly in the breeze. Small waves brush against stone, and the cooling ground feels rough beneath your sandals. Above the darkening water, the first stars emerge. The universe appears close enough to imagine as architecture. Greek thinkers inherit astronomical knowledge from older cultures while developing their own competing explanations. There is never one single Greek model accepted by everyone at every moment. Ideas overlap, disappear, return, and argue with one another. Some early philosophers seek natural explanations for celestial phenomena instead of relying entirely upon divine stories. Their proposals often seem strange today, but the important change lies in the method. The cosmos becomes something that reasoning might explain. By the 4th century B.C., Aristotle offers one of antiquity's most influential pictures of the universe. Earth rests near the center. Around it lie the moon, sun, planets, and stars, associated with nested celestial regions. The heavens possess an order fundamentally different from the changing terrestrial world below. To your ordinary senses, much of this seems reasonable. You do not feel Earth moving. Every day, the heavens appear to circle around you. Heavy objects fall toward the ground, which can be interpreted as movement toward the cosmic center. Earth therefore seems naturally central and stationary. Aristotle also argues that Earth is spherical, drawing upon observations available without telescopes. During lunar eclipses, Earth's shadow crossing the moon appears curved. Travelers moving north or south see different stars and notice familiar stars changing altitude. A spherical Earth explains these observations elegantly. The widespread modern tale that educated ancient people universally believed in a flat Earth badly misrepresents the history. Among Greek scholars, Earth's spherical shape became established long before the modern era. The harder question was whether Earth moved. Here, an extraordinary alternative appears. During the 3rd century B.C., Aristarchus of Samos proposes that Earth rotates and travels around the Sun. You can imagine how radical this arrangement feels. The ground beneath you seems motionless, yet Aristarchus asks you to picture it spinning while simultaneously carrying everything around the Sun. There is another consequence. If Earth changes position during the year, nearby stars should appear to shift slightly against more distant stars. This effect is called stellar parallax. Ancient observers cannot detect it. That absence presents a serious problem for a moving Earth. One possible answer is breathtaking. Perhaps the stars are enormously farther away than anyone assumes, making their parallax too small to observe. That answer happens to move toward reality, but without sufficiently precise instruments, it is difficult to demonstrate. Historians still discuss exactly how Aristarchus developed and defended his heliocentric proposal, because his principal work describing that system has not survived. You know the idea largely through later references. A revolutionary thought reaches you as an echo. Most ancient astronomers do not adopt it. This is not simply because they lack imagination. A stationary Earth fits everyday experience, accepted physics, and available observations reasonably well. Heliocentrism has not yet produced enough practical advantage to overthrow that framework. Meanwhile, measurement continues improving. Around the 2nd century BC, Hipparchus becomes one of the most important astronomical observers of antiquity. He works with earlier Babylonian records and Greek geometrical methods, helping combine traditions that had developed across different intellectual worlds. Hipparchus compiles information about stellar positions and brightness, although the exact relationship between his work and later surviving catalogues remains debated. His influence on positional astronomy is unmistakable. He also discovers something remarkably subtle. The celestial coordinate system slowly shifts over centuries. Today, you know this phenomenon as the precession of the equinoxes. Earth's rotational axis slowly changes orientation, somewhat like a spinning top whose axis gradually traces a circle. The cycle takes roughly 20,000 years. Hipparchus does not know the modern physical explanation, yet by comparing observations separated across generations, he recognizes that the sky's reference points are slowly changing. Once again, records reveal motions too gradual for one lifetime. This is one of astronomy's quiet powers. You inherit someone else's sky. By comparing it with your own, you can detect changes neither observer could witness directly. There is also a charmingly human story associated with Hipparchus. Later accounts connect his stellar cataloging with the appearance of a new star. Although historians remain uncertain about precisely what event motivated his work. Perhaps it was a nova. Perhaps the later tradition simplified something more complicated. Either way, the story captures a growing realization that the supposedly unchanging heavens might occasionally surprise you. Several centuries later, Claudius Ptolemy works in Roman Egypt, probably during the 2nd century AD. Alexandria provides the setting. Imagine sunlight reflecting from pale walls near the Mediterranean. Markets carry smells of oil, fish, spices, dust, and smoke. Greek intellectual traditions mingle with Egyptian, Roman, and older Near Eastern inheritances. Ptolemy develops an enormously influential mathematical treatment of astronomy. Earth remains stationary near the center, yet planetary motion creates difficulties. Mars, Jupiter, and Saturn sometimes appear to slow, stop, and move backward against the stars before resuming their usual direction. A simple circular orbit around Earth cannot reproduce this easily, so mathematical machinery becomes more elaborate. Ptolemy uses combinations of circles and geometrical devices to calculate planetary positions. A planet can move along a smaller circle whose center moves along a larger path. These constructions are often summarized using the word epicycles. Modern retellings sometimes portray this system as absurdly complicated nonsense, desperately protecting an obviously wrong idea. That is unfair. Ptolemaic astronomy is sophisticated mathematical science for its time. It provides useful predictions and works with the observations available to ancient astronomers. A model can be physically mistaken while mathematically effective. That distinction will become surprisingly relevant much later. Even modern cosmology relies upon models whose deeper interpretation can remain uncertain while their predictions work extremely well. For centuries, the Ptolemaic framework survives because it does something important. It calculates. You can predict planetary positions without knowing that Earth itself is a planet moving around the Sun. The heavens remain finite and ordered in this ancient picture. Beyond the planetary regions lies the sphere of fixed stars, unimaginably distant by everyday standards, but still conceptually part of a structured cosmic architecture. There are no known galaxies beyond the Milky Way. There is no expanding space-time. There is no measurable cosmic beginning. The universe, as understood through much Greek philosophy, is often eternal or organized according to principles very different from modern cosmology. Aristotle's cosmos especially resists the idea of a physical beginning in time. This matters because the question of cosmic origins will eventually become entangled with philosophy, theology, mathematics, and observation. For now, evidence favors stability. Night after night, stars return. Centuries pass, and constellations remain recognizable. If the universe is evolving, it does so on scales inaccessible to ancient human experience. Yet you have traveled an enormous intellectual distance. The sky is no longer merely a calendar. It has become geometry. Earth has acquired a shape and a proposed location within a larger structure. Planetary paths can be calculated. Stellar positions can be catalogued. Most importantly, competing cosmic models now exist. One places stationary Earth at the center. Another daring possibility allows Earth to move. The disagreement cannot yet be settled because the necessary evidence remains beyond the precision of available instruments, and so the older model endures. Centuries will pass. Empires will fragment. Languages will shift. Libraries will vanish. And manuscripts will travel enormous distances. The mathematical heavens of antiquity will survive this journey because scholars in another intellectual world will preserve them, criticize them, improve them, and measure the sky with increasing precision. The universe itself continues quietly overhead. Humanity's model of it is about to travel east and south before returning transformed. Centuries pass, and the old Mediterranean world changes around the astronomy it created. Political centers rise and disappear. Libraries scatter their contents. Greek becomes less dominant across former Roman territories, while new scholarly communities inherit fragments of ancient mathematics and philosophy. You follow those fragments eastward. By the 8th and 9th centuries, major centers of learning flourish across the Islamic world, especially under the Abbasid Caliphate. Baghdad becomes an important meeting place for scholarship drawn from several traditions. You arrive there on a warm evening. The day's heat still lingers in stone and packed earth, Lamps glow beside courtyards, while the air carries dust, cooking smoke, leather, and faint traces of ink. Somewhere nearby, a manuscript is being copied. The act seems quiet. Its consequences are enormous. Texts associated with Greek astronomy, mathematics, philosophy, medicine, and other fields are translated, studied, criticized, and developed alongside knowledge inherited from Persian, Indian, and local traditions. Ptolemy's astronomy becomes especially influential. His great astronomical work survives through this complicated movement of texts across languages and centuries. Scholars do not simply place it reverently on shelves. They calculate with it. They test it. They notice problems. This distinction matters because medieval Islamic astronomy was not merely a storage room between antiquity and Renaissance Europe. Astronomers improve observations, develop mathematical techniques, compile tables, refine instruments, and challenge parts of inherited planetary theory. You can see why accurate astronomy remains useful. Religious calendars require careful treatment of lunar cycles. Determining times for daily practices encourages mathematical astronomy and timekeeping. Geography and navigation also benefit from improved measurements. Yet curiosity exceeds immediate practical needs. People simply want to understand the sky. You climb onto a flat rooftop after sunset. The stone beneath your hand is cooling. Voices soften in the streets below. Above you, the same planets observed in Babylon and Alexandria continue their slow movements. The instruments beside you remain beautifully simple by modern standards. There is no electronic detector. There is no camera. There is certainly no computer politely complaining that your software requires an update. Instead, you might work with carefully graduated instruments designed to measure angles. Astrolabes become famous examples. Different forms of these instruments can help determine celestial positions, estimate time, solve geometrical problems, and represent relationships between the sky and an observer's horizon. Holding one feels very different from looking through a telescope. You are not magnifying a planet. You are measuring where it is. Precision becomes the quiet obsession. Astronomers such as al-Battani, working around the 9th and 10th centuries, produce improved measurements of solar and planetary behavior. His calculations influence later astronomical traditions well beyond his own cultural setting. Other scholars examine Ptolemy's assumptions more critically. By the 11th century, Ibn al-Haytham raises objections concerning aspects of Ptolemaic planetary models, particularly the relationship between mathematical constructions and physically plausible celestial motions. That problem is deeper than it first sounds. Suppose your mathematics predicts where Mars appears. Is that enough? Or should the mathematical model also describe something that could physically exist? You have encountered an early version of a question that will haunt cosmology repeatedly. A model can match observations while leaving reality strangely unclear. Centuries later, scientists will calculate invisible dark matter, inflationary fields, and dark energy while asking what these mathematical ingredients physically represent. The instruments change. The philosophical discomfort survives across the medieval Islamic world. Observatories eventually become increasingly ambitious institutions. One remarkable example appears at Moraga in the 13th century, in what is now northwestern Iran. There, Nasir al-Din al-Tusi and other scholars work within a major observatory, supported by substantial resources. Imagine approaching the complex at night. The air is cooler at elevation. Stone walls hold the day's fading warmth inside. Observers and mathematicians work among manuscripts, geometrical diagrams, and large instruments. Their purpose is not casual stargazing. They want numbers. 2C develops a mathematical construction now called the 2C couple. Through combinations of circular motions, it can generate an oscillating linear movement. The geometry may sound obscure beside the grandeur of galaxies, yet ideas like this matter because they provide alternatives to troublesome features of Ptolemaic astronomy. Later, mathematical similarities between Islamic astronomical models and those appearing in Renaissance European astronomy have generated extensive historical discussion. Scholars continue examining how particular ideas may have traveled and whether similarities demonstrate direct transmission in every case. The evidence is complicated. Manuscripts move in unexpected ways. Ideas can cross cultures without leaving neat receipts. Astronomical knowledge also develops farther east. At Samarkand during the 15th century, Ulugh Beg establishes an extraordinary observatory and supports highly precise stellar measurements. Its enormous instruments allow astronomers to determine celestial coordinates without telescopic magnification. You stand beside part of a monumental measuring structure. Cold night air touches your face. The stone feels smooth beneath your fingers. Stars cross the carefully marked geometry as observers compare their positions. The scale is impressive because precision requires physical size. Before electronics, making an angular instrument larger can allow finer measurements. Ulugh Beg's astronomical tables and star catalogue become important achievements of observational astronomy. The stars themselves remain points of light. Nobody can yet determine their chemical composition. Nobody measures reliable stellar distances. Still, their positions are being mapped with increasing care. Elsewhere, scholars investigate optics. Understanding how light behaves will eventually prove just as important as understanding planetary motion. Ibn al-Haytham's studies of vision and optics emphasize that sight occurs when light reaches the eye from external objects, helping move explanations away from older ideas that vision might involve rays emitted by the eyes. This seems unrelated to cosmology. It is not. Astronomy is fundamentally a science of received information. For most of cosmic history accessible to observation, you cannot touch the object you study. You collect whatever reaches you, usually light or another form of radiation. Understanding light, therefore, means learning how to interrogate the universe. Much later, spectroscopy will reveal what stars contain. Photography will preserve faint celestial images. Radio antennas will detect an invisible sky. Space telescopes will observe wavelengths blocked by Earth's atmosphere. Eventually, detectors will capture a microwave afterglow from the young universe itself. But those achievements require a long apprenticeship in light. Meanwhile, medieval European astronomy develops through monasteries, cathedral schools, universities, courts, and contact with translated scholarship. From roughly the 12th century onward, translated astronomical and mathematical works become increasingly available in Latin Europe. Ptolemaic cosmology becomes deeply embedded within university learning. Earth remains stationary. The celestial spheres remain ordered around it. To someone standing beneath the medieval sky, the arrangement still feels natural. You hear a bell in the distance. Smoke rises from hearths into cold evening air. Above rooftops without electric lighting, stars appear brilliant and numerous. Nothing visibly announces that Earth is moving. This point deserves patience. Later generations sometimes describe the geocentric universe as though one clever glance should have exposed its mistake. But your senses continue supporting it. If Earth rotates, why do you not feel the motion? If Earth travels around the Sun, why can observers still not detect annual stellar parallax? If the stars are sufficiently distant to hide that effect, then the universe must be enormously larger than commonly imagined. That possibility requires a dramatic expansion of scale. For many scholars, the established system remains intellectually coherent, yet difficulties accumulate. Planetary calculations require increasingly careful parameters, discrepancies between models, philosophical ideals, and observations invite criticism. Astronomers propose modifications. Nobody wakes one morning and discovers that medieval cosmology has suddenly collapsed. Scientific revolutions rarely behave that neatly. Old frameworks survive because they solve real problems. New frameworks struggle because they initially contain uncertainties of their own. You are approaching such a transition now. By the 15th century, European scholars possess ancient Greek astronomy enriched by centuries of mathematical development across several civilizations. Printed books will soon accelerate the circulation of ideas. Oceanic voyages will increase demands for astronomical navigation. Improved instruments will sharpen positional measurements, and one quiet scholar will rearrange the cosmos by moving Earth away from its privileged stillness. He will not discover the Big Bang. He will not even discover galaxies, but he will perform a conceptual act essential to everything that follows. He will allow the universe to become different from what ordinary human experience insists it must be. The stars remain overhead, patient as ever. For thousands of years, you have watched them move. Soon, you will seriously consider that perhaps they are not performing the greatest movement at all. Perhaps you are. By the early 16th century, you inherit a cosmos that is mathematically sophisticated, culturally familiar, and increasingly uncomfortable in certain details. Earth still occupies the center of the traditional astronomical system. The sun, moon, planets, and distant stars appear to travel around it. Yet generations of observations have created an awkward situation. The calculations work, but not always elegantly. You enter the world of Nicholas Copernicus, born in 1473 in the Polish city of Torun. He studies mathematics and astronomy alongside medicine, law, and church administration. Astronomy is only one part of his intellectual life. Imagine yourself beside him during a cold northern evening. Wood smoke hangs over darkened roofs. Your hands tighten against the chill. Somewhere beyond the town, the horizon lies black beneath an unusually clear sky. Mars glows with its familiar reddish light. Its strange wandering remains troublesome. Sometimes Mars moves eastward against the background stars, then it slows, appears to stop, reverses westward, and eventually resumes its earlier direction. Ancient mathematical astronomy can reproduce this retrograde motion. Copernicus asks whether the arrangement might become more coherent if Earth itself moves. The thought is not entirely new. Aristarchus had proposed a moving Earth many centuries earlier, yet Copernicus develops a far more extensive mathematical system around heliocentric organization. In 1543, the year of his death, his major work on celestial revolutions appears in print. You open such a book and smell paper, leather, dust, and ink. Inside lies a disturbing rearrangement. Earth is no longer stationary at the cosmic center. It rotates once each day. It travels around the sun yearly. The apparent daily sweep of the heavens can therefore be explained largely by Earth's rotation. The apparent backward movement of planets can emerge naturally from relative orbital motion. You can picture the effect while traveling along a road. When you pass a slower cart, that cart can appear to drift backward against the distant landscape, even though it continues moving forward. Something comparable happens when faster-moving Earth overtakes Mars. Retrograde motion becomes an effect of perspective. This is elegant. It is not yet decisive. Copernicus retained circular motions because circles possess deep mathematical and philosophical appeal. Consequently, his model still requires combinations of circles to match observations accurately. Heliocentrism does not instantly produce perfect predictions. There is also that stubborn old problem. No annual stellar parallax can be detected. If Earth moves around the Sun, nearby stars should shift slightly during the year. Copernicus must effectively place the stellar sphere at an immense distance. The universe grows larger because the evidence refuses to cooperate conveniently. Historians continue debating aspects of Copernicus's motivations, intellectual influences, and the pathways through which earlier mathematical ideas reached Renaissance Europe. The revolution bearing his name was not created in isolation. Knowledge rarely arrives without ancestors. Still, moving Earth changes the conceptual landscape. You no longer occupy the obvious center. That displacement will eventually become a recurring feature of astronomy. Earth will become one planet among several. The Sun will become one star among hundreds of billions in the Milky Way. The Milky Way will become one galaxy among an immense population. Even ordinary matter will eventually prove to be only a small fraction of the cosmic inventory. Humanity keeps losing central positions. The universe does not appear troubled by this, yet Copernicus alone cannot settle the argument. For that, astronomy needs better observations. You move toward the late 16th century and encounter Tycho Brahe, a Danish nobleman with an unusual personality and an extraordinary commitment to measurement. Tycho receives royal support for an astronomical complex on the island of Hven. There he builds large instruments designed to measure celestial positions with remarkable naked-eye precision. No telescope assists him. That invention has not yet entered astronomy. You climb beside one of Tycho's great instruments on a cold night. Metal and wood feel hard beneath your fingers. The air smells faintly of damp earth, smoke, and the sea surrounding the island. Assistants work carefully nearby. A planet crosses the marked scale. You record its position. Again and again. For years, Tycho understands something essential. If competing cosmic systems make different claims, better data may expose which description works best. He himself does not accept Copernicus's complete arrangement. Instead, Tycho develops a hybrid model in which Earth remains stationary. The Sun moves around Earth, and other planets move around the Sun. To modern ears, this may sound like unnecessary compromise within his own evidence. However, it addresses serious concerns. He still cannot detect stellar parallax. A stationary Earth remains physically plausible within contemporary understanding, and his system can reproduce many observational appearances associated with heliocentric planetary organization. There is no simple march from ignorance toward truth. Smart people disagree for good reasons. Then the heavens provide an unexpected disturbance. In November 1572, Tycho notices a brilliant new light in the constellation Cassiopeia. Today you understand the event as a supernova, the catastrophic explosion of a distant star. Tycho does not possess that explanation, but he measures the object's position carefully. It shows no detectable daily parallax that would place it among nearby atmospheric phenomena. The new light therefore appears to belong among the distant stars. This is deeply unsettling. Traditional Aristotelian cosmology treats the celestial region beyond the moon as essentially unchanging. Yet something new has appeared there. The supposedly immutable heavens have changed. A comet in 1577 creates another challenge. Tycho's measurements suggest that it travels beyond the moon, crossing regions where solid celestial spheres would become difficult to maintain literally. The architecture of the old heavens begins loosening, not collapsing, loosening. Then, in 1600, another figure enters the story through mathematics rather than spectacle. Johannes Kepler begins working with Tycho in Prague. The relationship is not especially peaceful. Tycho possesses superb observations. Kepler desperately needs them to test his ideas about planetary motion. After Tycho dies in 1601, Kepler gains access to the observational material necessary for his calculations. Mars becomes the stubborn centerpiece. Kepler attempts to fit Tycho's observations using circular planetary motion. The numbers almost cooperate. Almost. A discrepancy of roughly 8 arc-minutes remains. 8 arc-minutes is a tiny angle. You could easily imagine ignoring it. Kepler refuses. He trusts Tycho's observations enough to conclude that the model, rather than the measurements, must yield. That decision changes astronomy. After years of calculation, Kepler determines that Mars follows an ellipse rather than a perfect circle, with the Sun located at one focus. The ancient preference for perfect celestial circles finally breaks. Planets also move at changing speeds, sweeping equal areas in equal times. Later, Kepler discovers a mathematical relationship connecting orbital periods with orbital sizes. The solar system begins behaving according to quantitative laws. There is a quirky beauty in Kepler's journey because he reaches these powerful results while pursuing ideas that modern astronomy does not retain. He searches for hidden geometrical harmonies and initially tries arranging planetary distances using nested regular solids. The universe declines to cooperate. Kepler keeps calculating anyway. This combination of imaginative speculation and ruthless attention to data becomes one of science's recurring habits. You may begin with an idea that is wrong. The important question is what happens when nature disagrees. Kepler's ellipses describe planetary movement with remarkable success, but they do not explain what physically drives the planets. Why should Earth continue around the Sun? Why should Mars trace an ellipse? What invisible connection organizes the system? The answer requires another conceptual leap. Before that leap arrives, however, a small optical instrument will be pointed toward the heavens. Through it, the moon will cease to look perfectly smooth. Venus will reveal phases. Jupiter will acquire companions. And the Milky Way will begin dissolving into innumerable stars. You have moved, Earth. Now you are about to acquire new eyes. The new eyes arrive from an invention that was not originally designed to transform humanity's understanding of the universe. In 1608, spectacle makers in the Netherlands become associated with the first documented attempts to patent an instrument capable of making distant objects appear closer. News of the device travels quickly. By 1609, Galileo Galilei hears about the idea in Italy and begins constructing improved versions for himself. You meet him in Padua beneath a warm summer sky. Evening air enters through an open window. You smell oil from a nearby lamp and the faint dusty scent of worked wood and polished glass. In your hands rests an awkward tube. It does not resemble a modern observatory telescope. Its field of view is narrow. The lenses introduce distortions. Holding the instrument steady requires patience. Yet when you raise it toward the moon, the ancient heavens begin changing. The lunar surface does not appear perfectly smooth. Bright regions and dark boundaries shift as sunlight strikes features across the landscape. Galileo interprets these patterns as mountains, valleys, and irregular terrain. You are looking at another world. That simple realization carries philosophical weight. For centuries, influential traditions had distinguished the changing, imperfect Earth from supposedly perfect celestial regions. Now the moon resembles a place. It has geography. Galileo estimates the heights of lunar mountains by studying their shadows. The method is imperfect, but the principle is powerful. Light can reveal shape across astronomical distances. Then the telescope turns toward Jupiter. On January 7, 1610, Galileo records several small points of light near the planet. Their positions change during subsequent nights. Eventually, he realizes they orbit Jupiter. 4 moons become known to European astronomy: Io, Europa, Ganymede, and Callisto. You watch them through the telescope. They are tiny. Nothing about the view feels cinematic. You see bright points beside another bright point, trembling slightly in atmospheric turbulence. Yet their implications are enormous. Not everything circles Earth. A miniature system exists around Jupiter. This observation does not prove heliocentrism by itself, but it weakens the claim that every celestial body must revolve directly around your world. Galileo also observes Venus. Its changing phases provide an even more serious challenge to the traditional Ptolemaic arrangement. Venus displays a range of phases consistent with its moving around the Sun. Some geocentric alternatives, including Tycho's system, can accommodate this observation. The evidence, therefore, does not instantly select Copernicus over every competitor. Scientific arguments remain untidy. That is usually how real discovery works. Galileo observed sunspots as well, joining other early telescopic observers who study markings moving across the Sun. The supposedly flawless celestial body possesses visible irregularities. Even the Sun refuses perfection. Then you turn the instrument toward the Milky Way. To your unaided eyes, it appears as a pale mist crossing the darkness. Through the telescope, parts of that glow dissolve into enormous numbers of faint stars. The universe becomes crowded. For generations, humans have looked directly at these stars without knowing they were individually there. An instrument has revealed an invisible population hiding inside visible light. This pattern will repeat. Radio telescopes will uncover an unseen radio universe. X-ray observatories will reveal violent high-energy environments. Infrared detectors will peer through dust. Gravitational wave instruments will eventually sense distortions in space-time itself. Every new way of observing nature creates another universe layered upon the old one. For Galileo, however, even using the telescope as an astronomical instrument is controversial. Some critics question the reliability of what lenses reveal. Early telescopes can produce optical artifacts, and there is no long-established tradition proving that every unfamiliar telescopic feature corresponds to something physically real. This caution is understandable. Imagine being shown an imperfect new instrument and told it has overturned centuries of cosmology. You might want another look. Historians continue discussing the complicated mixture of scientific, philosophical, personal, and theological factors surrounding Galileo's later conflict with church authorities. Reducing the episode to a simple battle between science and religion loses much of its historical texture. The astronomical debate itself contained genuine unresolved questions. Galileo possesses strong evidence against traditional Ptolemaic arrangements, but he lacks a complete physical explanation for Earth's motion. He also incorrectly considers tides powerful evidence for Earth's movement. Even revolutionary scientists can be spectacularly confident about weaker arguments. The universe offers no immunity from human stubbornness. In 1632, Galileo publishes a dialogue comparing major world systems. The political and religious consequences become severe. In 1633, he is tried by the Roman Inquisition and required to abandon public support for heliocentric claims in the form he had defended. Yet astronomical evidence continues accumulating. Ideas are harder to imprison than people. Elsewhere, telescopes improve. Observers learn to grind better lenses and build longer instruments. Saturn presents one of the strangest early puzzles. Galileo sees unusual structures around it, but cannot resolve the rings clearly. At times, the features seem to change or nearly disappear. Saturn behaves like a celestial prank, performed at the expense of 17th-century optics. In 1655, Christian Huygens discovers Titan, Saturn's largest moon, using an improved telescope. He later proposes that Saturn is surrounded by a thin, flat ring separated from the planet. Another impossible-looking object becomes understandable through better resolution. The telescope is doing more than adding discoveries. It changes what counts as evidence. For thousands of years, astronomy depended primarily on naked-eye positions and geometrical reasoning. Now physical details become visible. Celestial bodies have surfaces, companions, changing features, and structures. The sky begins becoming a collection of worlds. But one enormous question remains: what keeps those worlds moving? Kepler has described planetary orbits mathematically. His laws tell you how orbital speeds and distances relate. They do not provide the complete underlying mechanism. Galileo, meanwhile, studies motion on Earth. He investigates falling bodies and develops ideas about inertia, challenging older assumptions about how objects naturally move. The terrestrial and celestial problems are slowly approaching each other. This convergence becomes crucial. Ancient cosmology often treats heaven and earth as fundamentally different physical realms. The new science increasingly suspects they belong to one system. You can test motion with objects near the ground. You can measure planetary motion in the sky. Perhaps the same principles apply to both. By the later 17th century, Isaac Newton will bring these strands together. Yet before you reach him, notice how much the universe has already changed without the stars themselves moving noticeably. You began with a stationary Earth surrounded by celestial perfection. Now Earth travels around the Sun. Planets follow ellipses. Jupiter possesses moons. The Moon has mountains. The Sun has spots. Saturn has a ring. The Milky Way contains innumerable stars. And still, almost nobody knows how far those stars truly extend. The visible universe remains largely without depth. Stellar parallax has still not been reliably measured. The stars could be immensely distant, but their distances remain uncertain. There is another limitation. Telescopes show you brighter and fainter points, but brightness alone cannot provide a straightforward distance. A faint star might be nearby and intrinsically dim, or it might be brilliant and extraordinarily remote. The cosmos refuses to provide convenient labels. You need new physical principles. You need better measurements. Eventually, you will also need to learn how to read the hidden information carried inside starlight. For now, you return to the telescope. The metal fittings feel cool beneath your fingertips. Your eye approaches the narrow eyepiece. Jupiter enters the field again, accompanied by tiny moons whose existence was unknown for almost all human history. They move silently. No crystal sphere carries them. No invisible hand needs to push them around each night. Somewhere within their motion lies a rule that also governs the moon above Earth and an apple falling toward the ground. Soon, those separate motions will become one idea, and when they do, the universe will cease being merely geometrical. It will become physical. By the middle of the 17th century, you inhabit a universe filled with motions that astronomy can describe, but cannot yet completely explain. Kepler has given you mathematical laws for planetary orbits. Galileo has transformed terrestrial motion and turned the telescope toward previously hidden celestial details. The pieces seem related. Someone must connect them. You travel to England in 1665, when an outbreak of plague disrupts ordinary academic life and temporarily closes the University of Cambridge. Isaac Newton leaves Cambridge and spends extended periods at his family home in Woolsthorpe. The setting is quieter than the scientific revolution surrounding it. You can imagine damp grass beneath your shoes after rain. Wood smoke drifts from the house. Leaves stir gently while clouds move across a pale English sky. Newton is in his early 20s. During this period, he develops important ideas concerning mathematics, optics, and motion. Although the familiar story of one miraculous year compresses a much longer intellectual process. And yes, there is an apple. Probably. Newton later recalls that seeing an apple fall helped prompt thoughts about gravity. The popular version, in which an apple strikes him dramatically on the head and instantly produces universal gravitation, is considerably more theatrical. History enjoys improving stories. Reality usually prefers notebooks. The deeper question is more interesting anyway. Why does the apple fall downward while the moon remains overhead? Perhaps the moon is falling too. Imagine throwing a stone horizontally. It moves forward while gravity pulls it downward. Throw it faster, and it travels farther before reaching the ground. Now imagine an impossibly fast projectile. Earth's surface curves away beneath it at the same rate that it falls. The projectile never reaches the ground. It is in orbit. The moon can therefore be understood as continually falling around Earth. This insight dissolves an ancient boundary. The force affecting objects near your feet may also reach into the heavens. Newton eventually develops this idea into the theory of universal gravitation. Every mass attracts every other mass. The strength depends upon the masses involved and decreases with the square of their separation. Earth pulls the moon. The moon pulls Earth. The sun governs planetary orbits through the same principle. Suddenly, Kepler's mathematical laws are no longer isolated patterns. They can emerge from deeper physical rules. In 1687, Newton publishes his great work on mathematical principles of natural philosophy. You open the heavy volume beneath candlelight. Paper feels slightly rough beneath your fingertips. Wax and smoke scent the room. Dense geometrical arguments cover the pages. There is nothing especially sleepy about the mathematics. The consequences are beautifully simple. One physics governs heaven and earth. The same universe extends from falling objects to orbiting planets. Newton's framework also allows astronomers to predict celestial motions with increasing precision. Comets provide a spectacular demonstration. For much of human history, comets have appeared suddenly, grown luminous tails, crossed familiar constellations, and disappeared. They seem like visitors from nowhere. Edmund Halley studies historical observations of several bright comets and recognizes similarities among appearances recorded in 1531, 1607, and 1682. Using Newtonian mechanics, he concludes that these are probably returns of the same object. He predicts another appearance around 1758. Halley dies before seeing the result. The comet returns. There is something quietly moving about, predicting an event beyond your own lifetime. You trust mathematics enough to leave a message for people not yet born. When the comet reappears, Newtonian gravitation gains another extraordinary success. The sky is becoming predictable through physical law, yet the universe still contains mysteries even Newton cannot resolve. What exactly is gravity? Newton can describe how gravitational attraction behaves mathematically, but he avoids claiming a complete mechanical explanation for its underlying nature. This uncertainty will persist in transformed form until Einstein changes the question centuries later. Even then, gravity will retain mysteries. Scientific explanations often replace one question with a deeper one. The 18th century now opens before you. Telescopes improve gradually. Astronomers discover more comets, measure planetary positions, and refine the dimensions of the solar system. A major goal remains detecting stellar parallax. If Earth truly changes position while orbiting the Sun, nearby stars should shift against distant backgrounds. Observers search. The effect remains elusive. The reason is not that Earth is stationary. The stars are simply much farther away than early astronomers imagined. This absence of parallax forces the cosmos outward. Then another discovery enlarges the known solar system itself. On March 13, 1781, William Herschel observes a small object through a telescope from his garden in Bath, England. At first, he suspects a comet. The object looks different from ordinary stars and changes position. Further observations reveal something astonishing. It is a planet, eventually called Uranus. It becomes the first planet discovered in recorded history, beyond those visible to unaided human eyes. You stand outside with Herschel. The night is cold enough to make your fingers stiff. Moisture gathers on nearby surfaces through the telescope. The New World appears tiny and unimpressive, yet Saturn is no longer the known planetary frontier. The solar system has doubled dramatically in scale. Herschel is not finished. With increasingly powerful reflecting telescopes, he surveys stars systematically and attempts to infer the structure of the Milky Way. He counts stars in different directions, assuming that roughly uniform stellar distributions and telescope reach can reveal the galaxy's shape. His resulting model is imperfect. Interstellar dust obscures distant stars and distorts the apparent distribution. The Sun's location is also difficult to establish from such observations. But the conceptual change matters. The Milky Way is becoming a physical structure that can be mapped. You are inside it. This is another quiet displacement. The glowing band across the ancient sky is not a decoration surrounding Earth. It is evidence of a vast stellar system containing your Sun. Herschel also discovers infrared radiation in 1800 through an experiment involving sunlight, separated into colors by a prism. He places thermometers across the visible spectrum and notices heating beyond the red region where his eyes see no light. Invisible radiation exists. This quirky experiment opens another doorway into astronomy. The universe sends information your eyes cannot detect. Eventually, infrared astronomy will reveal cool objects, dust-shrouded star formation, distant galaxies, and ancient light stretched by cosmic expansion. The telescope has begun escaping human vision. Historians still debate how best to interpret some early attempts to map the Milky Way because their assumptions, observational limits, and definitions differ from modern galactic astronomy. That caution matters. Herschel is exploring an unknown structure from inside it. Imagine trying to map an enormous forest while standing among the trees, unable to see through fog. That is approximately the problem. Still, the scale keeps growing. Newton's physics has connected Earth with the planets. Herschel's observations place the Sun among enormous populations of stars. Invisible radiation hints that nature contains information beyond ordinary senses. Yet the universe is still commonly imagined as fundamentally stable. Stars may form or change, planets may orbit, and comets may return. But the cosmos as a whole has no established measurable expansion. There is no observational evidence yet for a hot beginning. Even the word galaxy has not acquired its modern cosmological meaning. Those faint spiral nebulae visible through telescopes remain deeply puzzling. Are they small structures inside the Milky Way? Or could they be enormous stellar systems far beyond it? You cannot answer yet. To do so, astronomy needs something more than bigger telescopes. You must learn what stars are made of. You must measure their distances. You must preserve their images beyond the fleeting memory of an observer at an eyepiece. And eventually, you must discover that light itself carries fingerprints of matter and motion. Newton gave you laws connecting the heavens. The next generation will begin reading messages hidden inside the light those heavens send. As the 19th century begins, you know that the universe extends far beyond the solar system, but its true dimensions remain hidden. Stars still appear as points. Even powerful telescopes cannot show ordinary stars as detailed disks. Their distances remain difficult to measure, and their physical nature is only beginning to emerge. You need several new ways of seeing. One arrives through photography, another comes through spectroscopy, a third finally gives the stars depth. You begin in 1838 with Friedrich Bessel, working at the observatory in Königsberg. After centuries of failed attempts, he announces a successful measurement of stellar parallax for the star 61 Cygni. The displacement is tiny. You can imagine the patience required. Night air presses cold against the observatory walls. Metal instruments chill your fingertips. Oil and wood leave familiar smells inside the observing room. You measure the star. Months pass. You measure again as Earth travels to the opposite side of its orbit. The star's apparent position shifts slightly against more distant background stars. The movement is barely perceptible, yet it settles an ancient argument. Earth moves. More importantly, geometry now provides a direct route toward stellar distance. The measured parallax of 61 Cygni places it many light-years away. The stars are not lamps attached to a nearby celestial shell. Space between them is enormous. Even the nearest stellar systems lie so far away that their light takes years to reach you. For the first time, the universe gains reliable depth beyond the solar system. And then light reveals something even more remarkable. Isaac Newton had separated sunlight into a spectrum during the 17th century, but 19th century researchers begin discovering that spectra contain detailed physical information. In 1814, Joseph von Fraunhofer carefully maps hundreds of dark lines crossing the solar spectrum. You pass sunlight through a narrow opening and prism. A ribbon of color appears. Red melts into orange, yellow, green, blue, and violet. But thin dark marks interrupt the colors like missing notes in an otherwise continuous melody. At first, their full meaning remains unclear. Later experiments connect spectral lines with particular chemical elements. Gustav Kirchhoff and Robert Bunsen help establish that heated substances produce characteristic spectral signatures and that absorption can create dark lines at corresponding wavelengths. Suddenly, those marks become readable. You cannot travel to the sun. You cannot collect a jar of stellar material. You can still determine what stars contain. The 19th century quietly turns astronomy into astrophysics. Hydrogen reveals itself in stellar spectra. Other elements leave their signatures as well. The heavens are not made from some entirely separate celestial substance. The same chemistry found on Earth appears among the stars. An ancient boundary disappears again. There is a delightful historical twist here. Helium is identified in the Sun's spectrum before it is isolated on Earth. During a solar eclipse in 1868, astronomers observe a spectral line that eventually becomes associated with a previously unknown element. Humanity discovers something in the Sun before finding it beneath its own feet. The sky has become a laboratory. Spectroscopy also contains another gift. When a source of light moves relative to you, its spectral features can shift in wavelength. For astronomical objects moving away, spectral lines often shift toward longer wavelengths. For approaching objects, they can shift toward shorter wavelengths. This effect will eventually become essential to discovering cosmic expansion. But that revelation is still waiting. For now, you turn toward photography. Early astronomical photography is difficult. Photographic materials are insensitive by modern standards. Exposures can be long. Telescopes must track the sky accurately while Earth rotates beneath them. Yet a photographic plate possesses one great advantage over your eye. It can accumulate light. You may stare at a faint object and see almost nothing. A photographic exposure can gather photons over time, allowing features too faint for immediate vision to appear. The universe can now leave a physical trace. Astronomers no longer need to rely entirely on sketches and handwritten descriptions. Stars write themselves onto glass. By the late 19th century, photographic surveys begin recording enormous numbers of stars and nebulae. Women working at the Harvard College Observatory play crucial roles in organizing and interpreting this growing ocean of data. Williamina Fleming, Antonia Mori, Annie Jump Cannon, Henrietta Swan Leavitt, and others contribute to stellar classification and variable star research. You enter a room filled not with telescopes, but with plates. Glass surfaces click softly as they are handled. Paper rustles. Dust and chemicals leave a dry, institutional smell. The work can appear repetitive. It changes cosmology. Cannon helps develop the spectral classification sequence that eventually becomes familiar through the categories O, P, A, F, G, K, and M. The sequence is initially connected with spectral appearance rather than a complete understanding of stellar temperature. Later physics reveals its deeper meaning. The Sun becomes a G-type star, not the central lamp of creation, not physically unique. A star. Leavitt's work becomes even more important for measuring cosmic distances. While studying variable stars in the Magellanic Clouds, she recognizes a relationship between the periods of Cepheid variable stars and their intrinsic luminosities. The longer the period, generally, the greater the luminosity. This gives astronomers a powerful distance tool once the relationship is calibrated. You watch a Cepheid brighten and fade. It looks modest, yet its rhythm can tell you how luminous it truly is. Compare that intrinsic luminosity with how faint it appears, and distance becomes accessible. The universe has provided a kind of lighthouse. Without this relationship, one of the decisive discoveries in the Big Bang story becomes far more difficult. Meanwhile, another controversy grows. Telescopes reveal numerous fuzzy objects called nebulae. Some are clearly clouds of gas. Others display spiral structures. What are the spirals? One possibility places them within the Milky Way. Another proposes that they are separate island universes, enormous stellar systems comparable to the Milky Way and located at tremendous distances. The disagreement cannot be settled easily because astronomers still do not know the Milky Way's true dimensions with confidence. In 1920, the question becomes famous through a public discussion between Harlow Shapley and Heber Curtis in Washington. D.C. later remembered as the Great Debate. The label makes it sound rather more decisive than the evening actually was. Shapley argues for a very large Milky Way and generally places spiral nebulae within that broader cosmic framework. Curtis favors the interpretation that spirals are independent galaxies. Both possess evidence. Both also make mistakes. Science again refuses to assign one participant every correct answer. Shapley has already used globular clusters to argue that the solar system lies far from the Milky Way's center. This is another demotion for humanity. Copernicus removed Earth from the center of the planetary system. Now the Sun loses a privileged galactic position, but the spirals remain unresolved. Scholars still examine nuances of the Great Debate because later retellings often simplify what each astronomer actually claimed and how quickly the controversy was settled. The decisive evidence requires better distance measurements. That evidence will soon arrive from a new telescope on Mount Wilson in California. There, high above the lights and haze of growing Los Angeles, astronomers work with the 100-inch Hooker telescope. It is the largest operational telescope of its kind when completed in 1917. Imagine climbing into the observatory at night. Machinery hums softly. Cold mountain air enters whenever the dome opens. Metal, grease, dust, and electrical equipment create a distinctly modern smell. The telescope points toward the Andromeda Nebula. Through photographs, a young astronomer named Edwin Hubble begins identifying variable stars within it. Among them are Cepheids. Leavitt's stellar rhythm now becomes a cosmic measuring device. The resulting distance will place Andromeda far beyond the known scale of the Milky Way. Those faint spirals are not small clouds surrounding your galaxy. At least many of them are galaxies themselves. The universe suddenly fills with islands of stars. Millions will eventually become billions in human estimates, and later observations will reveal still greater populations across the observable cosmos. But distance alone is only half the coming revelation. Astronomers have also been examining the spectra of these mysterious galaxies. Many spectral lines appear displaced toward the red. The galaxies are telling you something through their light. You have learned to measure where stars are. You have learned what they contain. You have learned how far some celestial systems lie. Now you are about to measure how those systems move. And when distance and motion are finally placed beside each other, the apparently timeless universe will begin to change. Before those distant galaxies can reveal what the universe is doing, physics itself undergoes a transformation. You enter the 20th century carrying Newton's extraordinarily successful picture of gravity. For more than 200 years, Newtonian mechanics has predicted planetary motion, guided astronomical calculations, and helped reveal previously unknown worlds. It works beautifully, yet nature has begun leaving small clues that something deeper waits underneath. Mercury provides one clue. Its orbit slowly rotates through space, producing a shift in the position of its closest approach to the Sun. Most of this motion can be explained through gravitational influences from other planets. A small discrepancy remains. It is not large enough to overthrow Newton overnight. Science rarely receives such convenient invitations. Instead, the unexplained remainder sits quietly inside astronomical calculations, waiting for a theory capable of accounting for it. Then you meet Albert Einstein. In 1905, while working at the Patent Office in Bern, Switzerland, Einstein publishes several papers that reshape fundamental physics. One introduces special relativity. You walk through Bern beneath a cool evening sky. Street sounds echo between buildings. Coal smoke and damp stone linger in the air. A clock face glows somewhere above the street. Time seems perfectly ordinary. It is not. Special relativity begins from principles involving the laws of physics and the measured speed of light. Its consequences overturn familiar assumptions. Measurements of time and distance depend upon relative motion. Events simultaneous for one observer need not be simultaneous for another. Mass and energy are intimately related. The universe has not changed. Your concept of it has. Yet special relativity does not provide Einstein with a satisfactory description of gravity. Newtonian gravity appears to act across distance, while relativity has altered the structure connecting space, time, and causality. Einstein spends years searching for a deeper framework. By 1915, he arrives at general relativity. The central idea is both strange and elegant. Gravity is not simply an invisible force, pulling objects through an otherwise passive arena. Matter and energy influence the geometry of space-time. Objects then follow paths through that curved geometry. You can picture a planet orbiting the Sun not as something attached by an invisible cord, but as something following the natural geometry created by the Sun's presence. The analogy is imperfect. All simple analogies are. Still, space-time has become an active participant in cosmic behavior. This changes the question of the universe itself. Newton's laws describe objects moving within space. Einstein's equations allow space and time to possess large-scale structure and dynamics. You can now ask mathematically what space-time containing all cosmic matter should do. That question leads somewhere uncomfortable. Einstein initially favors a universe that is static on the largest scales. This preference is understandable. Astronomers have not yet established cosmic expansion. The night sky does not visibly stretch while you watch it. Stars and nebulae seem broadly stable. But when Einstein applies general relativity to the cosmos, gravity creates difficulty for a static universe. Ordinary matter attracts. A perfectly stationary cosmic arrangement does not emerge naturally. So Einstein introduces an additional term into his equations, the cosmological constant. With an appropriate value, this term can help support a static cosmic model. There is a charming historical irony here. The cosmological constant will later be associated with one of the greatest mysteries in modern astronomy. It disappears from fashion, returns decades later, and eventually becomes connected with the observed acceleration of cosmic expansion. Physics has a habit of keeping old ideas in storage. Meanwhile, general relativity begins surviving observational tests. One famous opportunity comes during the total solar eclipse of May 29, 1919. Expeditions led by Arthur Eddington and collaborators observe stars appearing near the darkened sun. General relativity predicts that the sun's gravity should bend their light, slightly shifting their apparent positions. You imagine standing beneath the eclipse. Daylight fades. The temperature falls against your skin. Equipment sits ready while the sky becomes an unnatural twilight. For a brief interval, stars near the sun become photographable. Analysis of the observations is announced as supporting Einstein's prediction. Newspapers transform him into an international celebrity. The historical details are more complicated than the legend. Researchers have long discussed the uncertainties of the measurements, the treatment of different photographic plates, and how strongly the 1919 observations alone established general relativity. Later experiments confirm gravitational light bending with far greater precision. The important point remains: gravity affects light because space-time itself possesses geometry. Now consider what happens if you apply Einstein's equations not merely to the solar system, but to everything. In 1917, Einstein publishes a cosmological model based on general relativity. The universe becomes an object of mathematical physics. This is a profound change. Earlier cosmologies often describe arrangements of celestial bodies within a cosmic structure. Relativistic cosmology asks about space-time as a whole. Can it expand? Can it contract? Can it evolve? Several researchers soon discover that dynamic universes arise naturally from Einstein's theory. In the early 1920s, Russian mathematician Alexander Friedmann finds solutions describing universes whose scale changes with time. Depending upon their properties, such universes can expand or contract. Friedmann is not observing galaxies racing away. He is following equations. At first, Einstein objects to his results, believing there is an error. After reviewing the work, he withdraws that particular criticism. The mathematics has opened a door. Another figure will soon walk through it. Georges Lemaitre is a Belgian physicist, mathematician, and Catholic priest. His combination of occupations sometimes surprises modern audiences, who prefer historical characters to fit into convenient boxes. Lemaitre refused to cooperate. He studies relativity and astronomy, eventually developing an expanding cosmological model independently. In 1927, he publishes work connecting relativistic cosmic expansion with observations of distant nebulae. He goes beyond mathematical possibility. He compares theory with the sky. By then, astronomers possess measurements of galactic motions that are becoming increasingly intriguing. Much of the observational foundation comes from Vesto Melvin Slipher at Lowell Observatory in Arizona. Beginning before the First World War, Slipher measures spectra from spiral nebulae. The task is difficult because these objects are faint. You join him inside a cold observatory. The telescope tracks slowly. Machinery makes soft, mechanical sounds. Night air smells dry, carrying the desert beyond the dome. Light from a spiral nebula falls onto spectrographic equipment. You wait. The exposure can require extraordinary patience. When the spectrum is finally examined, its lines are displaced. For many nebulae, they shift strongly toward longer, redder wavelengths. These red shifts are interpreted as evidence of large recessional velocities. Some galaxies appear to be moving away astonishingly quickly. A few nearby galaxies, including Andromeda, show blue shift because their local motions bring them toward the Milky Way. But the broader pattern increasingly points outward. Something large is happening. Lemaitre recognizes that general relativity can connect this pattern with an expanding universe. This does not mean galaxies are simply exploding through pre-existing empty space from one central location. The deeper idea concerns the changing scale of space between widely separated, unbound systems. There need not be a central point within ordinary three-dimensional space from which everything flies. Every sufficiently distant observer can see broadly similar expansion. This distinction will become essential when you finally approach the Big Bang itself. The Big Bang is not best imagined as an ordinary bomb exploding at one location. It concerns an early state of the universe everywhere. But you are not ready to travel backward that far. First, observation must become stronger. Hubble is measuring distances to galaxies using Cepheid variables. Other astronomers have already measured their spectral shifts. Soon, distance and recession will be compared systematically. The result will make cosmic expansion extremely difficult to ignore. You stand beneath the 20th century sky. To your eyes, nothing appears different. Orion still rises. The Milky Way still arches overhead. Andromeda remains a faint smudge under dark conditions, yet mathematics now says space-time can evolve. Spectra suggest distant galaxies are receding. The static universe is beginning to crack. For thousands of years, humanity has asked how the heavens are arranged. Now you are approaching a more unsettling question. If the universe is expanding today, what was it like yesterday? And what happens if you continue backward? The question now hangs quietly over astronomy. If space can expand, then the universe you see today may not resemble the universe of the distant past. But mathematics alone cannot settle the matter. You need distances. You need spectra. Most importantly, you need to discover whether the two are connected. You return to Mount Wilson in California during the 1920s, climbing above the growing lights of Los Angeles toward the enormous white dome of the Hooker telescope. At night, the mountain becomes cold. Pine and dry earth scent the air outside. Inside the dome, metal surfaces cool beneath your fingers, while motors and gears disturb the silence. Above you stands a 100-inch reflecting telescope. It gathers light that has traveled across distances almost impossible to imagine. Edwin Hubble uses this instrument to photograph the Andromeda Nebula and identify Cepheid variable stars within it. Henrietta Leavitt's earlier discovery now becomes crucial. The periods of these pulsating stars provide information about their intrinsic luminosities, allowing astronomers to estimate their distances. Andromeda turns out to be enormously distant. The conclusion becomes unavoidable. It is not simply a small nebula inside the Milky Way. It is another galaxy. The observable cosmos suddenly acquires tremendous depth. The Milky Way is no longer synonymous with the universe. You live inside one galaxy among many. Hubble continues measuring distances to other galaxies, although early values contain substantial errors because the cosmic distance scale is not yet properly calibrated. This is worth remembering. A revolutionary conclusion can emerge from imperfect measurements. Science does not wait for every decimal place to become correct before recognizing a powerful pattern. Meanwhile, astronomers already possess another kind of measurement. Vesto Slipher has spent years determining spectral shifts for spiral nebulae. Most show redshifts. These shifts are commonly expressed as recession velocities. Other researchers contribute additional measurements and interpretations. Now the two collections of information can meet. Distance, recession. In 1927, Georges Lemaitre has already combined available data and relativistic theory to derive a relationship between galactic distance and recession. His paper receives limited attention, partly because it appears in a relatively obscure Belgian journal. The universe has offered a clue. Distribution is apparently responsible for some of the delay. There is something wonderfully ordinary about that. A cosmic discovery concerning the expansion of space-time can still suffer from insufficient readership. In 1929, Hubble publishes a famous relationship between the distances of galaxies and their apparent recession velocities, using velocity data largely associated with Slipher's earlier measurements. More distant galaxies generally show larger recession velocities. Today, this relationship is connected with the Hubble-Lemaitre law. In its simplest nearby form, recession velocity is proportional to distance. You plot the measurements. The points do not form a perfect line. Astronomical data rarely behaves that politely. Yet the trend is visible. The farther away a galaxy lies, the faster it generally appears to recede with the cosmic expansion. The universe is not static. Space on the largest scales is expanding. You might instinctively picture galaxies rushing outward from one enormous explosion somewhere beyond the Milky Way. That picture is misleading. Imagine instead a collection of distant points embedded within a geometry whose scale increases. As the scale grows, separations between sufficiently distant unbound points increase. No ordinary central location inside that geometry is required. From one galaxy, distant galaxies recede. From another galaxy, the broad pattern looks similar. You have not discovered a privileged center. You have discovered expansion. A common analogy uses raisins inside rising bread dough. As the dough expands, every raisin becomes farther from distant raisins. No raisin needs to occupy the center of the expansion within the dough itself. The analogy has limits, but it helps remove the image of galaxies exploding into pre-existing emptiness. Cosmic expansion concerns space-time. This immediately invites the dangerous question you encountered earlier. Run the story backward. If galaxies are farther apart tomorrow than today, then they were generally closer together yesterday. Go farther backward, and average cosmic density increases. Continue farther still, and the universe becomes dramatically hotter and denser. The idea of a cosmic beginning begins emerging from physics rather than mythology. Yet astronomers do not immediately agree about what expansion means. Einstein himself had initially preferred a static universe. After observational evidence for expansion strengthens, static cosmology becomes increasingly difficult to maintain in its original form. A famous story later claims Einstein called introducing the cosmological constant his greatest blunder. Historians have questioned how securely that exact quotation can be documented. It is a useful reminder to be suspicious whenever history gives a famous scientist an unusually perfect line. Reality seldom writes dialogue that neatly. The expanding universe also creates a practical problem. Early measurements produce an expansion rate much larger than the value accepted today. If you naively calculate the universe's age from that early rate, you can obtain an age younger than some contemporary estimates for Earth and stars. That is awkward. Your universe should generally not be younger than the objects inside it. The contradiction does not destroy expansion. It reveals problems in the distant scale. Cepheid variables exist in different populations with different properties, and early calibrations do not properly account for these distinctions. Later corrections increase estimated galactic distances and reduce the inferred expansion rate. The universe becomes older. Measurement improves the story. Meanwhile, Lemaitre takes another conceptual step. In 1931, he proposes that the universe may have developed from an extremely compact initial condition that he describes using the idea of a primeval atom. This is not yet the modern Big Bang model. particle physics remains young. Nuclear processes inside stars are still being understood. There is no cosmic microwave background observation, yet the central historical insight has appeared. The universe may possess a physical past radically unlike its present. You can feel how strange this is. For most of astronomical history, celestial motion has been repetitive. The sun rises and sets. The moon cycles through phases. Planets return. Comets come back. Stars appear almost permanent. Now the universe itself acquires a direction through time. It was once different. That statement changes cosmology. But an expanding universe does not automatically prove a hot beginning. Alternative models remain possible. Perhaps matter is continuously created while expansion proceeds, allowing the universe to maintain broadly similar large-scale properties through time. Perhaps some mechanism avoids an initial hot state entirely. During the following decades, these possibilities become part of a genuine scientific dispute. The evidence is not yet decisive, and history is about to become considerably less peaceful. The 1930s give way to war. Physics advances rapidly through discoveries concerning atomic nuclei and particles. Sometimes, under terrible political circumstances, nuclear physics will unexpectedly provide tools needed to understand the early universe. Scientists begin learning how elements can be built and transformed. That knowledge raises another cosmic question. Where did the chemical elements come from? Stars can explain many of them, but perhaps the lightest elements preserve evidence from a time before stars existed. If the early universe truly was extremely hot and dense, it should not merely leave philosophical implications, it should leave physical remains. Something should survive, a measurable abundance, a fossil, perhaps even ancient radiation. You leave Mount Wilson as dawn approaches. The dome closes slowly behind you. The machinery becomes silent, and morning air begins warming the mountainside. Below, Los Angeles wakes without noticing that humanity's universe has changed. Earth once lost the center of the solar system. The sun later lost the center of the galaxy. The Milky Way has now lost its identity as the entire cosmos, and the universe itself has lost something even older. It has lost eternity in its familiar static form. You now inhabit a cosmos with a measurable history. The next task is to search that history for evidence of its earliest heat. Once the universe begins expanding in your equations, traveling backward becomes almost irresistible. You imagine galaxies drawing closer together as cosmic time reverses. Average density rises, radiation becomes more energetic, and temperatures climb beyond anything existing naturally around you today. Eventually, ordinary atoms cannot remain intact. Continue farther backward, and even atomic nuclei face conditions radically different from the present universe. The cosmic beginning is becoming a laboratory problem. During the 1940s, this possibility attracts George Gamow, a physicist with a gift for combining serious theoretical work with an unusually playful personality. You find him considering a simple question with enormous consequences. If the early universe was extremely hot, could nuclear reactions have occurred throughout space? The answer might explain where chemical elements originated. By then, nuclear physics has advanced dramatically. Scientists know that atomic nuclei can transform through reactions. They are beginning to understand how stars produce energy and how nuclear processes create elements. Now you apply similar reasoning to the universe itself. Imagine rewinding cosmic history. The familiar night sky disappears first. Galaxies become younger and closer together. Stars vanish because you have traveled to a time before they formed. There are no planets. There is no Earth. There is no quiet surface on which you can stand. Instead, matter exists within an increasingly hot environment filled with energetic radiation and elementary particles. There is no smell here. There is no breathable atmosphere. There is no sound traveling through ordinary air. Although pressure waves can move through the dense cosmic plasma of later early epochs, even the idea of touch loses its everyday meaning. You are using imagination to enter conditions no human body could experience. Gamow and his collaborators explore whether nuclear reactions in this early environment could manufacture the elements. Two researchers become especially important to this story. Ralph Alpher works with Gamow on calculations concerning the early universe. Robert Herman later collaborates with Alpher on the thermal consequences of that hot beginning. In 1948, Alpher successfully defends his doctoral dissertation concerning the formation of elements in an expanding universe. Gamow then turns the resulting research paper into one of physics history's better jokes. He adds the famous physicist Hans Bethe as an author, despite Bethe not having participated in the work, so the author list resembles the Greek letters alpha, beta, gamma, Alpher, Bethe, Gamow. A theory concerning the early universe acquires a pun. Alpher reportedly had mixed feelings about the joke because it risked obscuring his own contribution. Scientific humor, like cosmic expansion, does not affect everyone equally. Behind the joke lies serious physics. In a sufficiently hot young universe, protons and neutrons can participate in nuclear reactions as expansion continues. However, temperature and density fall. The nuclear furnace does not remain active indefinitely. There is a limited window. Modern Big Bang nucleosynthesis describes this period as occurring mainly during the first several minutes of cosmic history. The universe begins with matter too hot for stable complex nuclei to survive easily. As conditions cool, protons and neutrons combine. Hydrogen remains dominant. Helium nuclei form in substantial quantities. Smaller traces of deuterium, helium-3, and lithium also emerge. This is a remarkable prediction. The early universe should leave behind a characteristic chemical mixture. Not every element is created there. That part of the original ambition fails. The process encounters bottlenecks that prevent efficient production of large amounts of heavier nuclei. Carbon, oxygen, iron, and many other elements require later stellar processes. Stars become cosmic furnaces of another kind. Their interiors manufacture heavier nuclei across millions or billions of years, while stellar explosions and other events distribute and create additional elements. The Big Bang handles much of the light element foundation. Stars continue the chemical story. You are beginning to discover the universe twice again. First, matter physically evolves. Then humanity reconstructs that evolution from surviving clues. Helium becomes one such clue. Across suitable cosmic environments, its abundance is too large to be explained simply by ordinary stellar production without creating other problems. A hot early phase provides a natural explanation. Deuterium becomes especially valuable because it is fragile. Stars tend to destroy deuterium rather than manufacture large cosmic quantities of it. Its abundance therefore preserves information about conditions in the early universe. Modern measurements of primordial light elements provide an important test of Big Bang cosmology. The theory survives because nature approximately contains the mixture expected from those early nuclear reactions. There are complications. Lithium, in particular, refuses to behave perfectly. Predictions for primordial lithium abundance do not match observations of some old stars as neatly as cosmologists would like. This discrepancy remains known as the cosmological lithium problem. Perhaps stellar processes alter observed lithium. Perhaps nuclear physics requires refinement. Perhaps another ingredient is involved. Researchers continue investigating. The Big Bang model is powerful, not magically exempt from unresolved puzzles. During the middle 20th century, however, another cosmological framework offers serious competition. In 1948, Fred Hoyle, Hermann Bondi, and Thomas Gold developed the steady-state theory. The universe expands, but its large-scale appearance remains essentially similar through time because new matter is continuously created as space expands. The required creation rate is extraordinarily small. Locally, you would never notice matter popping dramatically into existence around the kitchen table. This model has an appealing philosophical feature. The universe has no special beginning. It can be eternal while still expanding. For some scientists, that elegance is attractive. The dispute is not simply between clever scientists and foolish ones. Both sides seek observational tests. In 1949, Hoyle uses the phrase Big Bang during a BBC radio broadcast while discussing competing cosmological ideas. The phrase eventually becomes the standard name for the theory he opposes. Whether Hoyle intended it primarily as ridicule has been debated, and historians caution against oversimplifying his tone. Either way, the name survives brilliantly. It is also misleading. Big Bang encourages you to imagine an explosion occurring at one location inside empty space. That is not what the model describes. As you run cosmic expansion backward, every sufficiently separated region of today's observable universe approaches an earlier, hotter, and denser state. There is no known ordinary point in space where you could place a flag and announce that everything exploded from there. Space itself participates in the evolution. There is another misconception worth gently removing. The successful Big Bang theory does not provide a complete scientific description of an absolute first instant. If you extrapolate classical general relativity backward, quantities can approach singular behavior. But such an extrapolation reaches conditions where quantum effects should become essential. General relativity is not a complete quantum theory of gravity. So when someone casually says, "Science knows exactly what happened at time zero," you may keep one eyebrow politely raised. Cosmology becomes increasingly uncertain as you approach the earliest conceivable intervals. Inflation, quantum cosmology, bouncing models, and other possibilities will later explore territory beyond the well-tested hot early universe. For now, Alpha and Hermann notice another consequence of cosmic heat. If the universe was once filled with intense thermal radiation, expansion should cool that radiation over time. It should not simply disappear. By the late 1940s, they estimate that a residual background should remain at only a few degrees above absolute zero. This prediction receives little immediate attention. Observational astronomy is not yet prepared to make it a central test. The signal would be everywhere, weak, cold, ancient. For years, it waits unnoticed. Meanwhile, radio astronomy is opening another window onto the cosmos. Antennas built for communication and radar research reveal that space contains powerful radio sources. Astronomers discover radio galaxies and other energetic objects. The universe looks less placid than optical astronomy once suggested. Observations of distant radio sources also begin challenging steady-state expectations because the cosmic population appears to change with distance and therefore with look-back time. Remember what distance means now. Light takes time to travel. When you observe a galaxy millions of light years away, you see it millions of years in the past. A telescope is therefore also a time machine. Look sufficiently far away, and cosmic history becomes directly observable. This principle will eventually allow modern instruments to see galaxies from the universe's youth. But the most decisive clue is already surrounding Earth. It passes through the atmosphere, it enters laboratories and antennas, it comes from every direction with extraordinary uniformity. Nobody initially recognizes it for what it is. Then, in the 1960s, a communications antenna in New Jersey develops an irritating background noise. Two engineers will try everything reasonable to remove it. They will clean equipment. They will examine possible interference. They will even confront some unfortunate pigeons. The noise remains, and hidden inside that quiet microwave hiss is light from a universe that existed long before the first star began to shine. By the early 1960s, the argument over cosmic history has become increasingly vulnerable to observation. The expanding universe is established. Evidence suggests that distant cosmic populations change across time. Nuclear physics provides a plausible explanation for primordial light elements, yet the most haunting prediction of a hot beginning remains undetected. Somewhere around you should be ancient radiation. You travel to Holmdel, New Jersey in 1964. On a quiet landscape stands an unusual communications instrument called the Holmdel Horn Antenna, built by Bell Telephone Laboratories for satellite research. Its broad metal structure points toward the sky. The surroundings hardly resemble the birthplace of a cosmological revolution. You hear insects in the grass and distant mechanical sounds. Summer humidity settles against your skin. The air carries vegetation, soil, and warm metal. Two radio astronomers, Arno Penzias and Robert Wilson, are working with the antenna. They encounter a persistent background signal. It is weak. It is also annoying. The excess antenna temperature corresponds to only a few degrees above absolute zero, but the signal appears regardless of where they point the instrument. That creates a problem. Ordinary astronomical radio sources usually have directions. Equipment problems usually have causes. This noise seems almost stubbornly universal. You begin checking possibilities. Could it come from New York City? Could military activity be responsible? Could the atmosphere produce it? Could some component of the receiving system be generating unwanted noise? The signal remains. Even seasonal changes fail to explain it satisfactorily. Then there are the pigeons. Birds have been occupying parts of the antenna and leaving what Penzias later describes, in memorable technical language, as a white dielectric material. The researchers remove the birds and clean the antenna. Cosmology has occasionally required heroic mathematics. On this occasion, it also requires cleaning pigeon droppings. The mysterious background persists. This is good news for cosmology, and rather unfortunate news for the pigeon's reputation. Meanwhile, only about 50 kilometers away at Princeton University, Robert Dickey, Jim Peebles, David Wilkinson, and Peter Roll are considering how to search for radiation left from a hot early universe. The two groups do not initially realize how perfectly their problems fit together. Then communication connects them. Penzias learns about the Princeton work and contacts Dickey. The implication becomes clear. The unwanted noise may not be local at all. It may be cosmological. In 1965, the Bell Labs measurement and Princeton interpretation appear in companion papers. The radiation becomes known as the cosmic microwave background. You have found the fossil, but to understand what you are detecting, you must travel backward again, not to the first second, not even to the first few minutes. You stop roughly 380,000 years after the hot Big Bang. By human standards, that sounds ancient. By cosmic standards, the universe is still an infant. Conditions are very different from today. Matter consists mainly of hydrogen and helium nuclei, electrons, dark matter, and radiation. The temperature remains high enough that ordinary neutral atoms cannot yet dominate. Free electrons scatter photons efficiently. Space is therefore filled with light, but that light cannot travel freely across enormous distances. Imagine fog. A car headlight inside dense fog produces light everywhere around you, yet you cannot see far because droplets repeatedly scatter the photons. The early universe behaves differently in its microscopic details, but the comparison captures the basic visual limitation. It is luminous and opaque. Then expansion continues. Temperature falls to roughly 3,000 Kelvin. Electrons increasingly combine with nuclei to form neutral atoms, especially hydrogen. Cosmologists call this process recombination, although the name is slightly odd because these particles are combining for the first time. Once free electrons become much less abundant, photons can travel enormous distances without repeated scattering. The universe becomes transparent. Those photons begin journeys that continue for more than 13 billion years. Some reach your instruments today. Cosmic expansion stretches their wavelengths along the way. Radiation that once possessed a temperature of thousands of Kelvin cools into microwave wavelengths. Today, its temperature is about 2.7 Kelvin above absolute zero. You are detecting ancient light from a surface known as the last scattering region. It is not light from the Big Bang's hypothetical first instant. That distinction matters. Earlier epochs remain hidden from ordinary electromagnetic observation because the universe was opaque to freely traveling photons. The cosmic microwave background is therefore something like the oldest light you can observe directly, and it comes from everywhere. Whichever direction you look, you are looking outward through space and backward in time toward regions where that ancient radiation last scattered. There is no single glowing wall somewhere beyond the galaxies. You are surrounded by your observable past. The discovery deals a devastating blow to steady-state cosmology. A nearly uniform thermal radiation field is naturally expected from a hot early universe. Explaining it within the classical steady-state framework is far more difficult. The Big Bang model becomes the dominant cosmological picture. Yet discovery does not end the argument. It improves the questions. How uniform is this radiation? Does it possess exactly the thermal spectrum expected from a hot early state? Are there tiny irregularities within it that could become the seeds of galaxies? Early measurements cannot answer these questions precisely. New instruments are needed. In 1989, NASA launches the Cosmic Background Explorer satellite, usually called COBE, above Earth's atmosphere. COBE measures the microwave background with unprecedented accuracy. One instrument determines its spectrum. The result closely matches an almost perfect blackbody spectrum, exactly the kind expected from thermal radiation. This is a spectacular confirmation. The universe was once genuinely hot. Another COBE instrument searches for tiny temperature variations across the microwave sky. In 1992, the team announces their detection. The variations are extremely small, roughly at the level of tens of millionths of a Kelvin. They are not observational clutter. They are precious imperfections. Without early variations in density, gravity would have little structure from which to build galaxies, clusters, stars, planets, and eventually observers. Perfect smoothness would have been cosmologically inconvenient. George Smoot, one of COBE's leading researchers, famously describes seeing the result in highly dramatic terms associated with viewing something primordial. The phrase becomes popular, though the scientific meaning is less theatrical. You are seeing a statistical map of tiny fluctuations. Still, their significance is profound. The early universe was nearly uniform, not perfectly uniform. Gravity amplifies those small differences over immense stretches of time. Slightly denser regions attract more matter. Dark matter begins forming gravitational structures. Ordinary gas later falls into these growing concentrations. The first stars ignite. Galaxies assemble. Clusters form. Eventually, one ordinary star develops inside one galaxy. Planets emerge around it. On one planet, chemistry becomes biology. Much later, two engineers struggle with unexplained antenna noise in New Jersey. The chain closes gently upon itself. Later missions improve the map. NASA's Wilkinson Microwave Anisotropy Probe, launched in 2001, measures temperature fluctuations with far greater precision. The European Space Agency's Planck mission, launched in 2009, provides still more detailed measurements from patterns within the microwave background. Cosmologists estimate the universe's age, geometry, composition, and early conditions. Modern values place its age at about 13.8 billion years, but scholarly uncertainty remains alive. Researchers continue debating tensions among different methods of measuring today's expansion rate. Measurements inferred from the early universe do not perfectly match several measurements based on the later cosmic distance ladder. This is known as the Hubble tension. Perhaps unknown systematic effects remain. Perhaps measurements will converge. Perhaps new physics is hiding inside the discrepancy. Nobody can responsibly declare the answer finished. The cosmic microwave background has therefore done something more interesting than simply prove an old theory correct. It has become a detailed photograph of conditions from which later cosmic structure emerged. You look at its modeled map, those tiny variations seem almost insignificant, yet inside them lie the gravitational beginnings of everything familiar. The universe has finally left you an image from its childhood. Now you can begin asking what happened even earlier, before atoms existed, before nuclei formed, and before the oldest light was free to travel. The trail leads backward into hotter conditions, and with every step, certainty becomes thinner. The microwave background has carried you almost 13.5 billion years into the past, but the oldest light still does not show the beginning. It shows a boundary. Beyond that boundary, the universe was opaque to freely traveling visible light. So, you must reconstruct earlier epochs indirectly. You become something like a cosmic archaeologist. Instead of pottery fragments, you examine elemental abundances, particle interactions, gravitational structure, and faint patterns embedded within ancient radiation. Each clue carries you farther backward. Begin again around 380,000 years after the hot Big Bang. Neutral atoms are forming, photons are escaping, and the universe is becoming transparent. Now reverse time. The temperature rises. Atoms break apart into nuclei and electrons. Continue backward toward the first few minutes, and even the familiar chemical universe disappears. You enter the era of primordial nucleosynthesis. Protons and neutrons collide within an environment far hotter than any ordinary furnace. There are no stars. There are no planets. There is no darkness in the everyday sense because energetic radiation fills space. Nothing here offers air to breathe or ground to touch. If you could somehow translate the environment into sensation, it would overwhelm every biological sense you possess. The cosmos itself is the furnace. During the first several minutes, expansion and cooling allow some protons and neutrons to combine into light atomic nuclei. Most ordinary matter ultimately remains associated with hydrogen. A substantial fraction becomes helium, with small amounts of deuterium and other light nuclei. The timing is delicate. If conditions remain sufficiently hot and dense for much longer, nuclear reactions could proceed differently. If expansion cooled everything too quickly, less helium would form. The chemical mixture therefore becomes a fossil clock. You can compare theoretical calculations with observations made billions of years later. The agreement between predicted and inferred primordial abundances provides one of the major foundations supporting the hot Big Bang model. Now travel backward past the first second. Your language becomes increasingly cautious. Temperatures climb into ranges where particle physics becomes essential. Neutrinos, electrons, positrons, photons, protons, neutrons, and their precursors participate in a rapidly changing thermal environment. At sufficiently high temperatures, familiar distinctions between matter structures lose their everyday meaning. Quarks and gluons become especially important. Today, quarks are confined inside particles such as protons and neutrons. In the extremely hot early universe, conditions allow matter to exist as a quark-gluon plasma. You have recreated tiny quantities of related states in powerful particle accelerators for extraordinarily brief moments. Collisions allow researchers to study matter under temperatures reminiscent of the young cosmos. It is a strange reversal. Humanity begins by staring upward with naked eyes. Thousands of years later, you build machines underground and smash particles together to understand what once filled all observable space. The universe is being reconstructed through experiments performed on one small planet. Continue backward, around the electroweak scale. Temperatures become so high that electromagnetic and weak interactions are understood within a unified framework. Earlier still, theoretical uncertainty grows rapidly. Physicists possess extraordinarily successful models of particle behavior and gravity. But these frameworks do not merge cleanly under every extreme condition. General relativity describes gravitation and space-time magnificently across enormous scales. Quantum theory governs microscopic physics with astonishing accuracy. Near the earliest conceivable conditions, you need both. That marriage remains incomplete. This is why the phrase, "the beginning of everything," requires care. The hot Big Bang model describes the evolution of the universe from an extremely hot, dense early state with remarkable success. It does not yet provide a verified account of an absolute first moment. There may have been one. There may be deeper physics. Current evidence does not allow you to speak with equal confidence about every earlier interval. One influential idea attempts to explain several mysteries appearing in conventional Big Bang cosmology. It is called cosmic inflation. The basic proposal is that the very early universe experienced an extremely rapid period of accelerated expansion. This does not mean matter simply raced through space faster than light in the ordinary local sense. The geometry of space itself changed dramatically. Inflation can help explain why the observable universe appears so geometrically flat and why widely separated regions possess remarkably similar properties. Without such a mechanism, distant portions of the microwave sky appear puzzlingly uniform, despite seeming too separated to have exchanged information within simpler early models. Inflation also offers a mechanism for producing the seeds of cosmic structure. Tiny quantum fluctuations in the early universe can be stretched to enormous scales. Later, gravity amplifies these variations. The faint temperature irregularities mapped in the microwave background may therefore preserve transformed traces of microscopic quantum fluctuations. Think about the scale of that claim. Something originating at extraordinarily tiny scales may eventually help determine where galaxy clusters form. The smallest physics becomes the architecture of the largest structures. Inflation is highly influential and consistent with several important observations. Yet the detailed mechanism remains uncertain. Researchers have proposed many possible inflationary models, and no specific underlying field has been definitively identified as the unique physical explanation. Cosmologists continue testing predictions involving primordial fluctuations and possible gravitational wave signatures. This is one of those places where confidence should become quieter. You know considerably more about the universe at 380,000 years than at unimaginably earlier moments. There is another famous mystery. Why does the observable universe contain much more matter than antimatter? Particle physics allows antimatter. When matter and corresponding antimatter meet, they can annihilate into radiation. If the early universe produced exactly equal quantities that later annihilated completely, the cosmos would look very different. Yet stars, planets, gas, and your own body exist. Some process apparently produced or preserved a small excess of matter. Physicists call the general problem baryogenesis. Several mechanisms have been proposed. None has been established as the final answer. The imbalance may have been tiny, roughly speaking. After enormous numbers of matter and antimatter particles annihilated, a small residual excess of matter could remain. That leftover becomes galaxies. You are built from a cosmic rounding error of astonishing importance. Another uncertainty concerns dark matter. Observations of galaxies, galaxy clusters, gravitational lensing, cosmic structure, and the microwave background strongly indicate the presence of additional gravitating matter beyond familiar atoms. Its microscopic identity remains unknown. It does not appear to interact with light in ordinary ways. You infer it primarily through gravitational effects. Dark matter becomes important early in cosmic structure formation because it does not couple to radiation like ordinary charged matter. It can begin forming gravitational structures under conditions where normal matter remains strongly influenced by photons. Later, ordinary matter falls into these dark gravitational frameworks. Galaxies grow inside invisible scaffolding. The stars that once seemed to define the universe now appear almost decorative compared with the unseen cosmic inventory. Ordinary matter represents only a small fraction of the total cosmic energy budget. Dark matter contributes much more. Dark energy contributes more still. This would have bewildered ancient skywatchers. They built cosmologies from what they could see. Modern cosmology discovers that most of the universe cannot be seen directly. There is a quirky echo of ancient uncertainty here. For millennia, humans imagined invisible substances and forces filling the heavens. Modern physics also invokes invisible components, but with a crucial difference. These components are inferred because quantitative observations demand gravitational or expansion effects that visible matter alone cannot explain. Names such as dark matter are admissions of ignorance as much as descriptions. You know what the phenomenon does better than what it is, and then you approach the theoretical frontier commonly associated with the Planck era, around 10 to the minus 43 seconds in naive backward extrapolations. Here, familiar theories can no longer be trusted independently. Quantum gravitational effects should dominate. Concepts such as ordinary space and time themselves may require modification. You cannot confidently continue the familiar movie backward. Perhaps quantum gravity removes the classical singularity. Perhaps a previous phase existed. Perhaps the universe emerged through some quantum process. Perhaps ideas not yet invented will replace all these possibilities. Scholars argue intensely because the available evidence becomes sparse. That uncertainty is not a weakness to hide. It marks the boundary between what observations strongly support and what remains theoretical exploration. You have traveled as far backward as current physics can guide you without pretending certainty. Behind you lies a well-tested hot cosmic history. Ahead lies a mist of quantum gravity and unanswered questions. The Big Bang has become clearer. The absolute beginning has not, having traveled as far backward as present physics safely allows. You turn around and face the universe that grew from those early conditions. The view is no longer simple. The cosmos once seemed to consist mainly of stars scattered through space. Modern observations reveal something stranger, dominated by components you cannot see directly. The first great invisible ingredient is dark matter. Its story develops gradually. In the 1930s, Swiss astronomer Fritz Zwicky studies galaxies within the Coma cluster and examines how rapidly they move. The galaxies seem to be moving too quickly for the visible matter alone to hold the cluster together gravitationally. Something appears to be missing. You imagine the distant cluster through an observatory telescope. The dome smells faintly of machinery, dust, and cold metal. Outside, mountain air touches your face while countless stars remain perfectly silent. The missing material itself is invisible. You notice only its gravitational consequences. Decades later, evidence becomes much stronger through measurements of galaxies. Vera Rubin and Kent Ford study how stars and gas move around galactic centers. You might expect orbital speeds to decline substantially, far from regions containing most visible matter. Rather, as outer planets move more slowly around the Sun. Many galaxies refuse to behave that way. Their rotation curves remain unexpectedly flat across large distances. Visible stars and gas cannot easily provide enough gravity under standard assumptions. Extended halos of unseen matter offer a compelling explanation. Other evidence accumulates. Galaxy clusters bend light through gravitational lensing more strongly than visible material alone would suggest. The microwave background contains patterns sensitive to cosmic composition. Computer simulations of structure formation also work much better when substantial non-luminous matter participates. Dark matter becomes central to modern cosmology. Yet nobody knows exactly what particle or substance constitutes most of it. Candidates have come and gone. Experiments operate deep underground, where rock shields detectors from much ordinary radiation. Other searches use particle accelerators or astronomical observations. So far, no universally accepted dark matter particle has walked politely into a detector and introduced itself. The mystery remains. Then the universe produces an even greater surprise. During the 1990s, two major research teams studied distant exploding stars known as Type Ia supernovae. These events can be standardized to estimate cosmic distances. The goal is partly to determine how gravity has slowed cosmic expansion. That expectation seems reasonable. Matter attracts matter. An expanding universe containing matter should experience gravitational deceleration, even if expansion continues indefinitely. You prepare photographic equipment and detectors beneath another dark sky. A distant galaxy contains a sudden point of light. For several weeks, one exploding white dwarf system can rival the brightness of billions of ordinary stars around it. Its light has traveled through expanding space before reaching your telescope. You measure its brightness, you measure its redshift. Then the pattern begins looking wrong. The distant supernovae appear dimmer than expected in a universe whose expansion is simply slowing. By 1998, results from the Supernova Cosmology project and the High Z Supernova Search Team point toward an astonishing conclusion. Cosmic expansion is accelerating. The universe is not merely getting larger. Its expansion has entered an accelerated phase. Something must account for this behavior within the cosmological model. The old cosmological constant returns. Einstein introduced it while seeking a static universe. Now, a positive cosmological constant can represent an energy density associated with empty space and drive accelerated expansion. The broad phenomenon becomes known as dark energy. The name sounds impressively explanatory. It is not. You have named the mystery. Modern measurements indicate that dark energy accounts for roughly 2/3 of the cosmic energy budget, while dark matter contributes around 1/4. Ordinary atomic matter provides only about 5%. Everything you directly recognize, stars, planets, oceans, trees, telescopes, and your own hands, belongs to that small fraction. Copernicus removed you from the center. Modern cosmology removes your familiar kind of matter from numerical dominance. There is almost a tradition developing. Researchers still debate what dark energy physically is. Perhaps it is a cosmological constant. Perhaps some evolving field contributes. Perhaps gravity behaves differently across enormous scales. The simplest standard cosmological model works extremely well, but the underlying nature of its dominant components remains obscure. Even the expansion rate itself presents a puzzle. Measurements based on the early universe, particularly within the standard cosmological model using microwave background data, yield a lower present expansion rate than several local distance measurements. This is the Hubble tension you encountered earlier. Improved observations have not simply erased the disagreement. Whether the tension indicates overlooked systematic effects or genuinely new physics remains an active question. Modern cosmology is precise enough to become uncomfortable with relatively small disagreements. That is progress of a peculiar kind. Meanwhile, your instruments have become almost absurdly sensitive compared with Galileo's tube. Radio astronomy reveals cold gas, pulsars, active galaxies, and the microwave background. X-ray telescopes expose hot gas and violent environments around compact objects. Infrared observatories peer through dust and detect light stretched by cosmic expansion. Space telescopes rise above atmospheric interference. The Hubble Space Telescope, launched in 1990, provides deep observations that transform studies of galaxies and cosmic history. Some exposures stare at apparently unremarkable patches of darkness. The resulting images contain thousands of galaxies. Darkness becomes crowded again. Then the James Webb Space Telescope begins scientific operations in 2022. Its large segmented mirror and infrared instruments allow astronomers to study extremely distant galaxies whose light has been traveling for more than 13 billion years. Because cosmic expansion stretches ancient light toward infrared wavelengths, Webb is particularly suited to examining the young universe. Early observations reveal surprisingly bright and developed galaxies at high redshift, encouraging active discussion about how quickly early galaxies formed. Some initial claims have changed as distances and interpretations improved. This is normal. The frontier is messy. You are watching scientific understanding adjust almost in real time as new data arrives. Yet light is no longer your only messenger. In September 2015, the LIGO detectors record gravitational waves from two merging black holes. The signal reaches Earth after traveling for more than 1 billion years. You do not see the collision directly with your eyes. Instead, extraordinarily sensitive instruments measure tiny changes in distance as a gravitational wave passes through Earth. Space-time itself trembles. Einstein's theory predicted such waves a century earlier. Now you can hear their mathematical equivalent translated into an audible chirp. The cosmos has gained another voice. Black holes themselves have also moved from theoretical curiosities toward observable astrophysical objects. Stars orbit an unseen massive object near the center of the Milky Way, providing powerful evidence for a supermassive black hole there. In 2019, the Event Horizon Telescope collaboration releases the first image of the shadow region surrounding a black hole in the galaxy M87. In 2022, it releases an image associated with Sagittarius A star at the center of your own galaxy. The images are blurred rings rather than science fiction portals. That makes them more remarkable. Humanity has built an Earth-sized virtual telescope by combining observatories across the planet. The species that once connected stars into imaginary animals now synchronizes atomic clocks to examine regions near event horizons, and planets around other stars have become ordinary astronomical discoveries. Thousands of exoplanets are confirmed. Some orbit within regions where temperatures could permit liquid water under suitable atmospheric conditions. Atmospheres of selected worlds can be investigated through spectroscopy. The ancient question of whether other inhabited worlds exist has entered observational science. No confirmed evidence of extraterrestrial life has yet answered it. The silence remains scientifically open. You now possess instruments capable of seeing galaxies from cosmic dawn, detecting colliding black holes, mapping ancient radiation, and measuring planets crossing distant stars. Yet the largest questions remain beautifully unfinished. What is dark matter? What drives accelerated expansion? Did inflation occur exactly as current models suggest? What happened before the hot early universe? Is life common? And what will happen to everything you see? The last question carries you forward rather than backward. You have reconstructed nearly 14 billion years of cosmic history. Now you allow the equations to continue. The galaxies drift farther apart. Stars age. Fuel diminishes. The universe enters futures no human being will witness. For the final time, your perspective expands beyond history into possibility. You have followed the universe backward until familiar physics begins to lose its certainty. Now you turn toward the opposite horizon. Instead of asking where everything came from, you ask what everything is becoming. The answer depends strongly upon the same discovery that surprised astronomers in 1998. Cosmic expansion is accelerating. If dark energy continues behaving approximately like a cosmological constant, the broad future appears increasingly isolated. Distant galaxies will continue receding. Galaxies sufficiently far beyond your gravitationally bound neighborhood will eventually become unreachable even in principle, as the expanding universe carries them beyond the region from which future signals can arrive. This happens slowly from any human perspective. Tonight, nothing dramatic changes. You can step outside beneath an ordinary dark sky and hear insects moving through grass. Cool air touches your face. Damp soil and vegetation carry familiar evening smells. The stars seem permanent. They are not. Even now, every star is spending a limited reservoir of usable nuclear fuel. The Sun has already existed for about 4.6 billion years. It should remain broadly within its current main sequence phase for roughly another 5 billion years before undergoing major changes. As hydrogen becomes depleted in its core, the Sun will eventually expand into a red giant. Earth's long-term fate during these stages involves uncertainties concerning solar mass loss, orbital evolution, and tidal interactions. But conditions suitable for present terrestrial life will disappear much earlier. You need not worry tonight. Your bedtime schedule remains safe. Far beyond the solar system, stars will continue being born while galaxies retain enough cold gas. But star formation cannot continue forever at present rates. Gas becomes locked into long-lived stars and stellar remnants, expelled from galaxies, or otherwise made less available for forming new stars. The universe gradually dims. The smallest ordinary stars possess astonishing longevity. Low-mass red dwarfs consume their fuel slowly and may survive for trillions of years. The present universe is only about 13.8 billion years old. In that sense, even the oldest cosmos you know is young compared with the stellar ages that may lie ahead. No red dwarf has yet had enough time to complete its entire natural evolution. Astronomers therefore predict portions of the remote future using physical models rather than direct examples. You are studying an era nature has never experienced. Eventually, conventional star formation largely ends. Existing stars fade or transform into remnants. White dwarfs remain after many lower-mass stars. Neutron stars and black holes survive other stellar deaths. The universe enters what is sometimes called a degenerate era. The phrase sounds mildly insulting. It is merely descriptive. Galaxies themselves also change. The Milky Way and Andromeda are gravitationally approaching each other despite overall cosmic expansion, because local gravitational interactions dominate on these scales. Their future interaction will transform both systems over billions of years. The exact sequence remains sensitive to measurements of their relative motions and to interactions involving other local group galaxies. Whatever final structure emerges, individual stars are unlikely to collide frequently because the distances between stars are enormous. Galaxies can pass through one another while most stars miss everything. The night sky during such an encounter would be spectacular. No human observer is expected to be present in anything resembling today's circumstances. Farther into the future, gravitational encounters can gradually rearrange stellar systems. Some objects may be ejected. Others can fall toward central black holes. The universe becomes increasingly sparse. Then the future grows more uncertain because it depends upon physics that has not yet been completely established. One major question concerns proton stability. Within the standard model of particle physics, an isolated proton is stable. Some proposed theories beyond the standard model allow proton decay over extraordinarily long timescales. Experiments have searched for such decay. None has been confirmed. If protons eventually decay, ordinary matter has an ultimate expiration process. If they do not, Certain remnants can persist much longer. This is where future cosmology becomes a landscape of conditional statements. If this happens, then that follows. If dark energy behaves this way, one future emerges. If its properties change, another becomes possible. The most conservative continuation of current observations leads toward something often called the heat death of the universe. The name sounds violent. The process is almost the opposite. It is the fading of useful differences. Thermodynamic systems can perform work when energy gradients exist. Hot regions can transfer energy toward colder regions. Stars shine because enormous physical differences remain available to drive processes over immense timescales. Usable free energy becomes increasingly difficult to access. The cosmos approaches a state of very high entropy, not a dramatic explosion, a gradual quieting. Black holes may become among the last major reservoirs of concentrated energy, yet even they are not necessarily eternal. In the 1970s, Stephen Hawking combines insights from quantum field theory with black hole physics and finds that black holes should emit thermal radiation. They can slowly lose mass for stellar mass and supermassive black holes. This process is absurdly slow under ordinary future conditions. The largest black holes could require timescales vastly exceeding even the long stellar era before evaporating. You wait through numbers that language barely handles comfortably. Trillions of years become tiny. Then trillions upon trillions become tiny. Eventually, if Hawking's description remains applicable across those enormous durations, black holes disappear through radiation. The universe becomes colder, darker, and emptier. Photons stretch toward longer wavelengths as space expands. Particles become increasingly isolated. Events grow rare. There are other possible futures. If dark energy changes with time, cosmic evolution could differ substantially. Certain hypothetical forms might produce increasingly extreme acceleration, potentially leading toward a scenario sometimes called the Big Rip. Current evidence does not establish such an outcome. Another historical possibility is cosmic recollapse, sometimes called the Big Crunch. In simpler models, sufficient gravitational attraction could halt expansion and reverse it. Present evidence for accelerated expansion makes a straightforward future recollapse less favored within the standard cosmological picture. Still, the ultimate future depends upon the true nature of dark energy and fundamental physics. Scholars continue debating those foundations because observation has not yet revealed what dark energy actually is. You have reached the peculiar edge of the story. The farther into the future you travel, the more your narrative becomes conditional. The same was true when you traveled toward the earliest conceivable moment. Certainty is strongest in the middle. You know that the universe was once hotter and denser. You know it expanded and cooled. You know light nuclei formed early. You know atoms emerged later. You observe ancient microwave radiation. You see galaxies across cosmic time. You measure expansion. You observe accelerated expansion. But at both ends, the beginning and the ultimate future, the path enters fog. Perhaps future instruments will clear part of it. New surveys will map enormous numbers of galaxies and measure cosmic structure with increasing precision. Gravitational wave observatories may open access to phenomena invisible through ordinary light. Improved microwave observations may search for subtle signatures from inflation. Future telescopes may examine the first generations of stars and galaxies more deeply. Particle experiments may identify dark matter, or they may not. Sometimes a non-detection is itself informative. You can imagine an astronomer centuries from now studying questions that currently lack names. That astronomer may look back at your era much as you look back at Galileo, not with mockery, with recognition. You are working with the instruments available. Galileo could not photograph galaxies. Hubble could not map the microwave background. Penzias and Wilson could not detect gravitational waves from merging black holes. Your own generation also possesses limits that future observers may find obvious only afterward. That humility connects the entire history. The Babylonian scribe pressing marks into clay was not separate from modern cosmology. The Egyptian observer waiting for a familiar star before dawn was part of the same human project. So were Aristarchus, Ptolemy, medieval astronomers, Copernicus, Kepler, Galileo, Newton, Herschel, Leavitt, Einstein, Lemaitre, Schleifer, Hubble, Alpher, Hermann, Penzias, Wilson, and countless less famous observers. Each inherited a sky, each added something, and gradually the question changed. Where do the stars move? What are they? How far away are they? What are galaxies? Why are galaxies receding? Was the universe once hotter? How early can physics take you? You began beneath an ancient sky that seemed eternal. You finish beneath a universe with history. Its age is measured in billions of years. Its visible structures span unimaginable distances, and its earliest directly observed light arrives as microwaves from every direction. The Big Bang was not discovered in one brilliant evening. No single telescope saw creation happen. No equation alone proved everything. The idea emerged slowly from thousands of years of accumulated observation, mathematics, argument, correction, and increasingly sensitive instruments. And even now, the phrase "beginning of everything" remains slightly ahead of what science can demonstrate. You can trace cosmic history toward an extraordinarily hot and dense early state. Beyond that, you meet questions. Perhaps that is the most appropriate ending. You return to the night sky. The air has become cooler, and the sounds around you soften. Somewhere beyond the glow of nearby homes, stars continue their slow passage across the darkness. You do not need to solve them tonight. You can simply notice that their light has traveled toward you through a universe still unfolding. The hydrogen in distant stars belongs to an ancient cosmic beginning. The heavier elements within your body were shaped by generations of stars that lived before the sun existed. You are resting inside that same history. The galaxies continue drifting through expanding space, quietly beyond your awareness. Ancient microwave light continues passing through the room and onward into the darkness. Nothing asks you to follow it, for now the long journey can become still. The universe keeps expanding, the stars keep shining, and beneath them you can finally rest.